Hello.
Okay, 100 participants are there already. That's
Good
great.
afternoon to everyone. A very warm welcome on this very novel celebration of World Quantum Day, which was launched globally on 14th April, that is yesterday. And we at PRL are celebrating this event today, that is on 15th April 2021. This is a new initiative started by some 67 plus countries starting from this year and aiming at more celebrations and more activities in time and years to come. And PRL is also joining this noble initiative. The idea of celebrating this World Quantum Day is to spread awareness to educational, students, institutions, universities, colleges, and even at school level about the importance of quantum science, which is now, leading to next gen technologies called quantum computers and quantum internet and whatsoever. So idea is to spread curiosity through awareness, outreach, and this kind of conferences. And the date so chosen, that is 14th April, is also a very unique date in a sense. That is a 4.14. That is the date, and the idea behind this is it is a rounded number of Planck's constant, that is 4.133 something. And we all know the importance of Planck's constant in quantum mechanics. And to start with the scientific temper in students' mind, this is the first question one should be asking to the students, young students especially, those who are joining or entering in the BSc level physics courses. That what is the importance of Planck's constant in quantum mechanics? And that is how journey starts of their understanding of quantum physics, which is leading to their advanced learning and understanding of quantum research or quantum science, quantum technology, etc. This event is also a humble attempt to have various talks on the theme of quantum information, quantum computation, quantum clocks, computing, etc., atomic clocks. And to add further into this, I would like to invite the chairperson of our Atomic, Molecular, and Optical Physics Division at PRL, Professor R.P. Singh. Professor R.P. Singh, over to you.
Thank you, Bhusit. Welcome to all of you for joining the meeting. Nowadays, it's very tough to join the online meeting. So many meetings going on almost every day. Each day we are having number of meetings. So you have joined in a good number. Thank you very much for joining the meeting. So welcome to Quantum Science and Technologies Applications to Modern Atomic Physics meeting. As Bhusit already pointed out, this meeting has been organized to celebrate World Quantum Day. So looking at the importance of quantum science and technology to uh, this day or to our society, at PRL also we have started a robust quantum science and technology program, and it covers all the aspects of quantum science and technology. So we have labs working in quantum communication, quantum sensing, and quantum metrology. It's experimental program as well as theoretical program at PRL. So it's very well thought out program at PRL when it comes to quantum sensing technology. So there are two labs working in quantum communication and quantum sensing and metrology. And there is one lab working in quantum materials, rather defect centers in crystals for quantum sensing and harvesting energy uh, from sun. Okay, how you can increase the efficiency of solar cells using quantum technology. And another lab, very unique. So there they can control electron dynamics, nuclear dynamics. They can control the atomic wave packet to control the molecular reaction. So as you know, everybody is reading about quantum computer, quantum computer. First problem, what quantum computer is going to do the molecular simulation. And already it has been tried out by Google. So that was the first problem this quantum computer attempted. And if you want to do experiments, that is simulation. Quantum computer is simulation. If you want to do experiments, this lab at PRL is well equipped that to do that kind of experiment. So we have very robust experimental program as well as theory. Our faculty, Professor Vijaya Sahu, is very versatile. He works in all aspects of quantum science technology, including quantum simulation, quantum computation, quantum sensing, atomic clocks, whatnot. He has touched almost all the fields. So that is our quantum science and technology program at PRL. Now regarding this meeting, quantum science and technologies, applications to modern atomic physics. So in this meeting or in this seminar, whatever you call, we have 6 speakers. Okay, and it's very good mix again. We have 3 theory speakers, theoretical aspects they will be covering, and we have 3 who are hardcore experimentalists. So Dr. Subhadeep Day works on atomic clocks. Bodhadit Santra is atomic interferometry for gravitational sensing. He works on like simulating a complex process using atoms, analog quantum computer, you can say, using atoms. And our own faculty at PRL, Dr. Rajesh Kushwaha, he is working on this controlling electron and nuclear dynamics to change the molecular reactions to produce new molecules. So that kind of work is being done. So, and they would be talking about their work. And we have Professor Das, well-known theoretical atomic and molecular physicist, and he has studied like a BEC, optical lattice, and now he's involved in quantum computation and all sorts of things. We have Vindhya Arora, and many body physics he works on. Prasanna, after working on many body physics, now he's more involved into this molecular simulation, as he told. So we will hear all the talks, and thank you everybody for agreeing to give the talks and joining the meeting. With these words, I invite our chief guest, Mr. Anil Bhardwaj, Director PRL, to inaugurate the meeting and share his thoughts for the day. Professor Anil Bhardwaj.
धन्यवाद तुषार सिंह। नमस्कार, अभिनंदन, स्वागतम। आप सभी को विश्व क्वांटम दिवस की बहुत बहुत बधाई, शुभकामनाएं। Very good afternoon and a very warm welcome to all joining us live for the meeting on quantum sciences and technologies, application to modern atomic physics, being hosted by Physical Research Laboratory today. This meeting is to cherish the start of celebrating April 14th as the World Quantum Day. The World Quantum Day is a bottom-up initiative from quantum scientists around the world, and PRL has already joined this initiative and is hosting this meeting as a part of this celebration today. In our college or university days, we have studied quantum physics or quantum mechanics and has worked with quantum states. But now the word quantum, if you see, has changed and has affected everything in our life. Whether it's science or technology, we now call it as quantum science, quantum technology. Computation has become quantum computation. Communication has become quantum communication. Information has become quantum information. Simulation has become quantum simulation. Algorithms have become quantum algorithms. Metrology has become quantum metrology. So much so, even chemistry, now we have quantum chemistry, where we talk about molecular quantum mechanics or basically chemical systems. Optics has become quantum optics. Dots have become quantum dots. So you name anything and it has a quantum attached to it. And earlier, we used to tell the physicists who used to work in quantum mechanics as a quantum physicist, but now we have quantum technologists, quantum engineers. So if you look at this scenario and try to extrapolate this to sports, you know, and we already say quantum jump. Probably we may be saying quantum race or quantum swimming to say. So the word quantum has come up in a big way in our life. And if you really start looking at even in terms of the area of social media, and I was just thinking about now we have Twitter, and what it will happen when quantum is added to the Twitter. It may become a Twitter, or even this YouTube could become quantum YouTube or QTubes, or even your Instagram would become Quantagram kind of things. And it has come to so much so that in our reality, now we talk about quantum reality or quantum field. And on a lighter side, I should say that now time is called quantum time. And so this day is called quantum day. So quantum is going to affect and has affected our life in a big way. And wishing you all a very happy quantum day. As Professor R.P. Singh mentioned, PRL has been working in the area of quantum science and technology for many years, looking at photonics and optics, entanglement of photons, and working now in quantum communication and quantum metrology. And this is jiving well with ISRO's initiatives, which are started in a big way, and in the area of quantum science and technologies. And along with the other ISRO centers and those units, PRL is playing a big role in the area of space-bound quantum communication. For today's meeting, we have 6 excellent speakers who would be covering broadly the topics covered under the word quantum, whether you call it quantum computing, quantum simulation, quantum metrology, quantum clocks, quantum control of molecular processes, quantum sensors, and quantum science and technology. And I thank all the speakers, Professor Bhanu Das, Dr. Prasanna, Dr. Subhadeep De, Dr. Bindya Arora, Dr. Rajesh Kushwaha, and Dr. Bodhadin Santra for accepting our invitation and be with us today in this celebration. I also thank my colleagues, Professor Vijay Sahu, Professor R.P. Singh, Dr. Bhushit, and other members who have been working in organizing this meeting, as well as the people who are taking care of technical requirements. I would like to request all of you to please follow COVID protocols and follow the guidelines given by various departments, ministries, and Government of India, because COVID is all around and we have to be very careful, wearing our masks and keeping social distances. The so-called Hindi couplet which says, "Do gaj ki duri, mask hai jaruri." So once again, a very warm welcome to all of you for this meeting on quantum science and technologies, application to modern atomic physics. And I'm sure that this is going to excite many of those who have been working in these areas, as well as those who are thinking of starting to work in these areas. With this, I declare this meeting open and request the Professor Vijay Sahu to conduct the meeting. Thank you. Thank you very much. Dhanyavad.
Yeah, thank you, Professor Anil Bharadwaj, for encouraging us and motivating us for this kind of science. As it was mentioned, we have 6 speakers, and among which we have a very experienced and eminent personality, Professor Bhanu Pratap Das, who had just assumed director position yesterday at TCG Crest, Calcutta. That's a newly formed institute. So Professor Anu Pratap Das is a very well-known personality at the international level in the atomic and molecular physics community. He had done his Bachelor of Science from IIT Kharagpur in 1974. Then he moved to US for doing MSc and PhD from State University of Newark, Albany. In 1981, he completed his PhD, and after that, he was, for a brief time, he was a lecturer at University of California, Riverside, and then he was also a research associate at the Max Planck Institute of Quantum Optics, Munich, Germany, and also at University of Notre Dame, Indiana. Then he took over the position as assistant professor at Colorado State University and Utah University. And then for some time, he was also lecturer at Oxford University before moving to India. So he moved to India in 1991. Then he spent 2 years in IIT Bombay. Then he moved to IIA Bangalore, where he spent his rest of his research career, like from 1993 to 2015. And there he was also acting director, I think from 2014 to 2015. And then he took retirement and moved to Tokyo Institute of Technology, TIT, Tokyo, Japan. And he just got retirement from there just recently, and then he has taken up this new job of a director position of this newly formed institute called TCG CREST, where he is going to do this quantum computing. And he's also American fellow for his seminal contributions to the theory of parity and time reversal violations in atoms in the context of probing standard model of particle physics. So with this, I would like to also congratulate him for starting this new innings of his career. So we wish all the best for his this new position. And with this brief introduction, and okay, he's also, it happens that he's my PhD thesis supervisor. I just wanted to mention that. With this brief introduction, I would like to now request Professor Das to share his slides and present his talk.
Okay. Thank you very much, Professor Sahu. So can you all hear me? Okay.
Yes,
okay.
we can.
Okay, yeah. So let me begin by thanking the organizers of the event, in particular, Professor Bharadwaj, Professor Bijay Sahu, Professor R.P. Singh, and Dr. Bhushit for organizing this unique event in India. And this is, yesterday was the World Quantum Day. And I think it's very timely. What we are witnessing now is the second quantum revolution, especially with the emergence of quantum computing and information. And I think, so this is a celebration of the rise of quantum mechanics. And, quantum mechanics now has assumed a very important part in our lives, and both academic and social. So let me now begin my talk. So I think, okay.
So Bhushit will present for you, and you can just, Bhushit, can you share his slide?
Yeah, sure.
Yeah. Hello? Hello?
Yeah, Bhushit is sharing your slide.
Yeah. Okay, fine. Thank you. Okay, all right. So the title of my talk is Quantum Computing, Present and Future. And I have listed my collaborators, as you can see, Dr. Prasanna, Professor Mukherjee, Professor Bijay Sahu, some of my collaborators, and I have a number of collaborators from Japan as well. And the last name that you see is Professor Nakamura, who was the inventor of the superconducting qubit. And we have been collaborating with him in doing actual quantum computation. So now can I have the next slide, please? Yes, so this is an outline of my talk. I'll first begin by saying something about classical computation and then give you a brief idea of quantum mechanics, an extremely brief idea of quantum mechanics, and then introduce some of the basic concepts in quantum computing. I mean, quantum computing is the marriage of classical computing and quantum mechanics. So so I'll explain some simple ideas in quantum computing, and then some applications of quantum computing to atoms, which is a real quantum mechanical system, and then finally conclusions and outlook. So the next slide, please. All right, so let me begin by saying something about classical computing. Classical computing is the is the regular computing that we do. So that is based on bits, and bits can take two values, either 0 or 1. So classical computation is done in terms of bits, which take on the values of 0 or 1. Now, physically, one represents a bit in terms of transistors, and the two states. The state is a very important concept when we talk about computation. So the two states of a classical computer are 0 and 1, and they can be represented as the off and on states of a transistor. So 0 would correspond to the off state, and 1 would correspond to the on state of the transistor. So we should think of bits as the basic states of a classical computer. Yes, next slide, please. All right, now this is the model of a classical computer. You can see that that bits here are made of transistors. The two states, 0 and 1, corresponds to different states of the transistors. And gates are also built from transistors. And then we combine bits in the form of inputs and outputs. And we combine those bits with gates, like the AND gate and the NOT gate, NOR gate, and so on, to have what we call a circuit. So a circuit consists of bits and gates, and the computations are done using bits and the gates, you see. So that is basically the model of a classical computer. Now, a question that one could ask is, can we make a quantum computer in a similar way? Obviously not the same way, but in a similar way. That means we have inputs and outputs, which would be in the form of the quantum counterpart of bits, which we call qubits, and gates, which would, or quantum gates, which would be the counterpart, the quantum counterpart of gates, you see. So is that possible? So this is something that some people thought about. In particular, Feynman thought about that. So can I have the next slide, please? Yes, I mean, in 1981, so in 1981, Feynman came up with this idea that it's possible to have, that it may be possible to have a quantum computer, and using qubits and quantum gates. And the qubits and the quantum gates, of course, would be made in a quantum mechanical way. So qubits would not be transistors, but rather made up of atomic or subatomic particles. So, I mean, he's famous for this statement that if you want to make a simulation of nature, you would better make it quantum mechanical, because ultimately nature is made up of atomic and subatomic particles, which are quantum mechanical in nature. So this was the idea that he had in the early 1980s. And there have been developments after that. And not too long ago, say about 10 years ago or so, John Preskill, who is currently the Richard Feynman Professor of Theoretical Physics in Caltech, and a very big proponent of quantum computing, he said that what is really exciting about quantum computing is that we have good reason to believe that a quantum computer would be able to efficiently simulate any process that occurs in nature. Well, that's a very optimistic statement. We will find out, I mean, when quantum computers start operating, we will find out whether the optimism of Preskill is correct or not. Okay. So the next slide, please. All right, so before I talk about quantum computing as such, let me just mention a few basic points about quantum mechanics, which most of you probably know. I mean, those of you who are not physicists probably know about it as well, because you may have taken, courses in quantum mechanics. So so quantum mechanics explains matter, at the microscopic level, that is atomic or subatomic level. And the most important quantity that we have in quantum mechanics is the wave function, which is also represented as a state vector. So the state vector is in terms of a ket. I mean, you can see a vertical line, a psi, and then a greater than sign. So that is called a ket. So you can have many vectors, psi1, psi2, and they form a vector space. And they basically are different states of a system, of a physical system. And then for each vector space, there is a dual vector space, which is a less than sign. And then you have the quantity, and then a vertical sign that's called a bra. So now, the wave function itself doesn't have a physical interpretation, but psi star psi is called the probability density. That is the probability per unit volume or unit length or whatever. And if you integrate over the entire volume, that is psi star psi, if you integrate over the entire volume, that would be the probability of finding the system in a particular space. And that we take as 1. And in terms of bra and ket, the integral is given as bra psi followed by ket psi. So that's equal to 1. Now, you can have an operator which represents a physical quantity acting on a state vector to give you another state vector psi prime. And its counterpart in the dual vector space is the adjoint of the operator acting on the corresponding bra vector to give you the bra vector psi prime. So we know how an operator acts on a state vector, and we also know how the adjoint operator acts on the bra vector. And any quantum, so once you find the wave function or the state vector, then we can find the property, a quantum mechanical property of a system, so which I call as O, which is basically the integral of psi star, because psi can be complex, psi star O psi, integrated over the entire volume, and in the bracket notation, it's bra psi O ket psi. Okay, now the next slide, please. Okay, now, so now that I've introduced the concept of a state vector or a wave function, I'll tell you what the important or the basic equation of quantum mechanics, which is the Schrödinger's equation. That's given by equation 1 and 2. So, you can have two different states of the system, two different state vectors of the system. So they correspond to different states, and they satisfy equation 1 and 2. So each of them satisfies the time-dependent Schrodinger's equation. All you have to do is to multiply the first equation by C1 and the second equation by C2, and then add them up and you get equation 3. So you can clearly see that if psi1 and psi2 are solutions of the time-dependent Schrodinger equation, then C1 psi1 plus C2 psi2 is also a solution. So that's the superposition principle, or the linear superposition principle, which holds in the case of quantum mechanics, because the Schrödinger's equation is a first-order differential equation in time. Now, a classical system which is governed by Newton's second law, which is a second-order differential equation in time, is not linear. So quantum mechanics is a linear theory, as we just have seen, and so the superposition principle is one of the hallmarks of quantum mechanics. It's a very important thing about quantum mechanics. So the next slide, please. Yeah. So now I can introduce this idea of qubits. So now that we've talked about wave functions or state vectors, now let's think about a physical system that can be in one of two possible states, 0 or 1. Then we would call that physical system as a qubit. Okay. So a qubit can be in two possible states, 0 or 1. So now 0 is represented in terms of a column vector 1, 0 and 1, 0, 1. Now, a general qubit state is given by psi, which is alpha 0 plus beta 1. Okay. So because of the linear superposition principle, you can write a state as a linear combination of two states, 0 and 1. And alpha and beta in general are complex numbers, and where the modulus alpha square plus modulus beta square is 1. So basically, the probability of finding the system in state 0 is mod alpha square. The probability of finding the system in state 1 is mod beta square. Now, so if we have two qubits, then you see, if you have one qubit, the basis states are 0 and 1. But if you have two qubits, the basis states would be 0, 0, 0, 1, 1, 0, and 1, 1. 0, the first 0 is for the first qubit, and the second 0 is for the second qubit, and so on. So if you have two qubits, you have 4 basis states. And then the general state of the general 2-qubit state is ket psi, which is alpha 0, 0, beta 0, 1, gamma 1, 0, and delta 1, 1. So, so when you do a measurement of the system, then the system is going to collapse to one of these basis states, and with the probabilities alpha square, beta square, gamma square, and delta square. So the sum of all the probabilities is 1. Okay, so the next slide then. Right, so you see that we have talked about 1 qubit states, 2 qubit states. Now, if you have 3 qubits, then you'll have 8 basis states, 0, 0, 0, 0, 0, 1, and so on. So 3 means 2 qubit basis states. So now let's compare the bits and the qubits. So if you have, so if you take, say, 1 qubit, then you have 2 basis states. So, but if you have a bit, you have only 1 basis state. So if you have 2 bits, then 2 basis states, but you'd have, if you have 2 qubits, you'd have 2 square basis states. So this way, if you have n bits, you have n basis states, but you'd have 2 to the power n qubit basis states. So as you increase the number of states available for computation for a given number of qubits is much more than the corresponding bit states. I mean, if you have something like, say, 3 bits, so that, 3 basis states for bits, then you'd have 8 basis states for qubits. So the number of states that are available for computation increases exponentially as you increase the number of as you increase the number of qubits. So with qubits, one can perform more computations than the same number of bits. Okay, the next slide, please. Yeah. Okay, now let me explain this idea of quantum entanglement. The idea of quantum entanglement and superposition are related. So, you can only entangle 2 or more things. You can't entangle a single thing. So if you take 2 qubits, as I mentioned earlier, the 2 qubit state psi has 4 basis states: 0, 0, 0, 1, 1, 0, and 1, 1. So I've used superscripts here to denote the qubits. So 0, 1 means the first qubit is in the 0 state. 0, 2 means the second qubit is in the 0 state, and so on, you see. So let's start with a 2 qubit state, which is the first line, and of course it's normalized. So the sum of all the modulus, the coefficients is 1. So that's because the probability is 1. So now all you have to do is to do some very simple algebra. So rewrite psi in a way that is shown in the second line. So then if you assume the condition beta over alpha is equal to delta over gamma, then what you find is that psi can be written as a product of 2 states, that is phi 1 and phi 2. Phi 1 depends only on the first qubit, and phi 2 depends only on the second qubit. Okay, so these are called separable states. That means you've written the general qubit state as a product of the first qubit state and the second qubit state, you see. Now that was only possible because you assumed beta over alpha is equal to delta over gamma. Now that's a very special condition. That's not generally true. So if that is not true, then you cannot write psi as a product of 2 separable states. That means you can't write ket psi as a product of 2 states, the first of which depends on first qubit and the second that depends on the second qubit. So then we say that the states are entangled. So the condition for entanglement is that beta over alpha is not equal to delta over gamma, you see. Now this is very, very simple arithmetic. You can easily check it. Now, of course, in general, beta over alpha is not delta over gamma. So when you, consider a 2 qubit state, which is a superposition state, then for the most part, it is entangled. So most of the linear superposition states for 2 qubits is entangled. And of course, a few of them are not entangled. So you see, quantum entanglement arises as a special case of the superposition principle. So now this is very important. I mean, quantum entanglement is absolutely necessary for quantum computing, for quantum communication as well. Okay, the next slide, please. Okay, now the idea of measurements, as I think I had briefly mentioned it, that is, if you have a qubit state that is represented by alpha 0 plus beta 1, then when you do a measurement, then the system collapses either to 0 or to 1 with probability alpha square or beta square. Okay, so although a qubit is a linear superposition of 2 states, the result of the measurement would be for a single state because it collapses to a single state. Now that's important to keep in mind. So this holds for any number of qubits. Okay, the next slide, please. Yeah. Now this is the basic idea of what I call quantum parallelism. That is, quantum computing is intrinsically parallel. So you can see that by taking, say, 4 qubits, then you'll have 16 basis states, 0, 0, 0, 0, and so on. So now let's say that you want to, let's say one of them is the password. One of these 16 things is the password, and you want to find the password, you see. Now, if you use bits, that is in classical computing, you'd have to look at them one by one, sequentially, you see. But if you do it on a quantum computer, you can treat all of them together in parallel. So you see, because of the linear superposition principle, a quantum computer operates in a parallel way, in a very natural way. It's naturally parallel. So, and then you can use a suitable algorithm like the Grover algorithm to find which is the correct password by discarding the 15 incorrect passwords, you see. So, whereas in a quantum computer, you deal with one state at a time. Here, you can deal with multiple states at the same time. So that means it is intrinsically parallel. And if you can find the right problem, you can gain in computational speed. Okay, next slide, please. All right, now remember that when we talked about a regular computer, we had bits and gates. So bits are, in the counterpart of bits in quantum mechanics is qubits, which we've just talked about. Now gates. Now, as you've seen in quantum mechanics, if you have a state, and then through an operator, you can go to another state. Okay. Now, so what we do is, instead of a state, we think of that as a qubit. So then the operator will be like the gate. So the operators in quantum mechanics can be represented as gates in a quantum computer. All right, so you see, state in quantum mechanics corresponds to a qubit for a quantum computer, and gate corresponds to an operator. So that means operator A acting on phi gives you psi. So that means a gate which is represented, a gate which you can represent by A will act on a qubit phi to give you another qubit state psi, you see. Now remember that the initial state is normalized because the probability is 1. So the final state should also be normalized. I mean, it belongs to the same vector space. It's also normalized. So that's the conservation of probability. So the fact that bra psi ket psi is 1 can be written as bra phi A dagger A ket phi is equal to 1. So, okay, so that means that so A is unitary, so the gate has to be unitary, you see. So gates are represented in terms of unitary operators. Okay, so the next slide, please. All right, so now, as I said, quantum gates are represented as operators, so which are basically, you can write in terms of matrices. So the X corresponds to the NOT gate, which is 0, 1, 1, 0. So what it does is, you can easily check that if X acts on 0, it gives you 1. So that's like the NOT gate. And if it acts on 0, it gives you 1. So there's another gate called the Hadamard gate, which is H. That's given by this matrix 1, 1, 1 minus 1. So when this acts on state 0, it gives you 0 plus 1 over root 2. So gates can act on qubit states to give you other qubit states, or they can act on a qubit state to produce a linear superposition. Okay, then you can also have rotational gates, which is given in the last line, where the gate would depend on some parameter theta. Okay, let's move on now. Next slide, please. Okay, yeah. So those are 1 qubit gates. You can also have 2 qubit gates, and the best known is what is called the C0 or the CX gate. So here you have 2 qubit states. So if the first qubit is 0, then the second qubit remains unchanged. And if the first qubit is 1, then the second qubit is flipped. The 0 becomes 1 and the 1 becomes 0. So this is what we call a control NOT gate, you see. So you have 1 qubit gates which act on 1 qubit states. You can also have 2 qubit gates. You can also have 3 qubit gates and so on. So very often we would need not just 1 qubit gate, but also 2 qubit gates. Okay, so let's move on. Next slide, please. Okay. Yeah. So now that I've introduced this idea of gates and qubits and gates, now let me talk about the different quantum computing models that we have. One is called a universal quantum computer that has qubits and gates. And DiVincenzo mentioned the criteria of a universal quantum computer. He is one of the pioneers in the field of quantum computing. He said a universal quantum computer should have scalability. That means you should be able to increase the number of qubits, and then you should have initializing qubits. That is, when you initialize qubits, it has to be properly defined, you see. And they should have long decoherence times. Now remember that when you entangle qubits, you want to keep it entangled for a long time, you see. Now that is called the decoherence time. I mean, so if you lose the entanglement, that means you'll be losing the coherence time also. So then you should have what are called universal quantum gates. That means you should have a set of gates so that you can combine them to perform any unitary operation. And you should have measurement capability. So these are the 5 criteria pointed out by DiVincenzo. Now there's another model which is called the quantum annealing computer. And this uses qubits, but it doesn't use gates. So what it does is that the system is allowed to evolve, and it'll naturally evolve to its most stable state, the ground state. So this is very good for finding like the ground state energy of a system. And this idea was first proposed in Tokyo Institute of Technology, with which I was associated for 6 years, just retired from there, by Nishimori and Kadowaki in 1998. And a company called D-Wave in Canada built the first quantum computer was built by D-Wave. That was a quantum annealing computer based on Nishimori's ideas. And now they have produced a quantum computer with 2,000 qubits. And a few years from now, they will have 5,000 qubits, you see. Now, this is well suited for optimization problems, meaning problems where you want to minimize something or where you want to find the most stable configuration. Not just scientific problems, but also social problems, like traffic control and various things like that. I mean, you could also use it for selecting the best cricket team. I think now that there are so many good players in the Indian cricket team, you can use a quantum annealing approach to find what would be the most suitable team from the given number of players, okay? But it's not as wide a scope as a universal quantum computer, because the gates will allow you to control things. So, but if you want optimization problems, finding the most stable configuration, then annealing probably is the best. Okay, the next slide, please. Okay, now, as I mentioned earlier, bits are made up of transistors, but not qubits. Qubits are made up of actual physical systems like atoms, ions, and so on. So the first prototype quantum computer that was produced in the lab came from the idea of Sirac and Zoller in 1995. It was produced by Wineland's group in the same year, and it's one of the works that led to Wineland getting the Nobel Prize. And here, the 2 states of an ion, the ground state and the excited state, which can be controlled by using a laser, are the 2 qubits. So the ground state is like 0 and the excited state is like 1. and they can be combined by using lasers, you see. So the ions that are good for such for quantum computers are calcium plus and ytterbium plus. The world's best trapped ion is made up of ytterbium plus, and that was made by IonQ. It's a company in the US, and the best computer that we have now is a 32 qubit trapped ion system produced by IonQ, and it has the best quantum volume, which is about 4 million. Now, the quantum volume measures the performance of a quantum computer regardless of what technology it is based on. So the quantum volume basically depends on how many qubits that computer can use and to what extent the errors can be reduced. So a computer will have a high quantum volume if the number of qubits are large and the number of errors are small, you see. So at the moment, the trapped ion computer produced by IonQ seems to have the best quantum volume. Okay, so the next slide then. Yeah, so then we also have what are called superconducting qubits. So those were the qubits that were first realized in the lab by Nakamura at the University of Tokyo, Riken. And his idea of making superconducting qubits. So basically, he identified two different directions of current flow, clockwise and anti-clockwise, as the two states of a qubit, 0 and 1. So in a superconductor, the current can flow in two different directions, and they correspond to two different states of the qubit, to put it very simply. So the most advanced technology that we have today is using superconducting qubits. But there are other platforms, ultra-cold atoms, silicon, quantum dots, photonics, and there are other possibilities as well. So each of them, each has its strengths and its weaknesses. Some are scalable, that means you can use a large number of computers, large number of qubits, sorry. Some where the decoherence time is large, in some cases it's not large, and so on. So there are various things that we have to look at when we decide on a particular platform for the qubits. Now, in terms of in terms of the current best superconducting qubits, IBM has 65 qubits, which in principle one could use through the IBM Q program, through the cloud. And IBM has a roadmap. They plan to have 1,000 qubits by 2023, and then extend that to 1 million qubits. Of course, photonic quantum computers are also scalable, and they have some advantages too. I think ultra-cold atom qubits are also scalable, so are silicon quantum dots scalable. But in terms of decoherence time, there are problems with silicon quantum dots. Ultra-cold atoms are pretty good in terms of the decoherence time. All right, okay, next slide, please. Okay, I'll just mention that quantum supremacy is one of the things that we want to achieve through a quantum computer. So quantum supremacy basically means that, it's a case when a quantum computer outperforms a classical computer. So the first case of quantum supremacy was demonstrated by Google using the Sycamore 53-bit superconducting qubit processor. And the problem they chose was a pseudo random number generator. And it was estimated to be 10,000 years on a classical computer. But IBM said that, with its most powerful computer, it can be done in 2.5 days. But the Sycamore quantum computer took 200 seconds. Now, there are, of course, many challenges. The errors can come from the qubits. They can also come from the gates. So those errors were there, so they have to be resolved in the future. Just to give you an idea of the numbers, so this problem involved 1,113 qubit operations, that is 1 qubit operations, and about 430 qubit, 2 qubit operations. Next slide, please. Yeah. Now, the second quantum advantage came from a group in China. They used a photonic quantum computer, and it's basically what's called the boson sampling problem using photons. So I'll not go into the details, but you have multiple inputs and outputs. So you allow a lot of photons to enter and a lot of photons come out, and then you look at the probability distributions of the photons that have come out in a particular mode. And so this involves lots and lots of computations, and it's estimated that it will take 2 billion years on a classical computer, but it actually took 3 minutes on the photonic computer that was built by the University of Science and Technology China group. Okay, so this was in 2020. Next slide, please. Yeah. Now, in terms of applications of qubit technology, as we have seen, qubits are absolutely necessary for quantum computing, whether it's the universal type or the annealing type. Now, what we know now is that we have an algorithm for factoring numbers, large numbers, okay? And we also have that's called the Shor's algorithm. We also have algorithms for doing database searches, the Grover's algorithm. And one can also do simulations. You can simulate atomic and molecular processes, which I'll talk about. And that, in the long run, will have implications for drug discovery and design of new materials. And one can, from a mathematical point of view, solve differential equations, which will find applications in climate modeling. And then, if one applies machine learning in quantum computers, that will lead to quantum machine learning. These are all possible. And in terms of quantum communication, basically, as many of you know, for quantum communication, what we need are entangled qubits. Okay, so, and in this field,
I mean, to finish the talk in another 5 minutes.
Okay. So quantum communication is well known. So there's quantum key distribution, which was also demonstrated by ISRO recently, and one can think of quantum internets. Okay, next slide, please. Yeah. So, okay, I'll skip the quantum circuits part. Okay, next, please. Yeah. So next, please. Next. Yeah, okay. All right. Now, I'll just take some time, now that you know that it is possible to do computations, using a quantum computer. But the algorithms are mostly for mathematical problems, like factoring numbers and database searches and so on. Now, what about doing an actual quantum mechanical problem in a quantum computer? So let's take an atom where the Hamiltonian is given by the first line, and that satisfies, say, the Schrodinger's equation, H psi 0 is E0 psi 0. E0 is the ground state energy, and psi 0 is the ground state wave function. So the energy is the expectation value. I'm assuming that the wave functions are normalized. Now, because of the electron-electron interaction term in the Hamiltonian, E square over Rij, it's not possible to solve this equation exactly. So what we do is that we approximate the wave function psi 0 by what's called the mean field wave function phi 0. The mean field is an approximation corresponds to taking the two-body interaction and approximating it by an average one-body interaction. So which I call VMF, meaning the mean field. It's the average potential that each electron sees due to all the other electrons. So we have, and that state phi 0, it's a determinant built out of single particle states like phi 1, phi 2, etc. And the single particle states satisfy equation 3. Now, of course, the mean field potential depends on the individual states phi. So it has to be solved self-consistently, meaning in an iterative manner till it converges, you see. So these can be done on a classical computer. They've been routinely done for atoms and molecules. So one can do this on a classical computer. So the next slide, please. Yeah. So now the important thing is now that we can find phi 0, we can solve for the individual states and get phi 0. Then the exact wave function psi 0, we write it as a unitary operator as a function of theta acting on phi 0. Now this is an important step, because once you write it in terms of a unitary operator, then you can express them in terms of gates. So once you do that, then you can see the energy consists of phi 0, which are basically built out of single particle states. And then you have those in the brown, the ket, then you have u dagger h, u theta. Now, the u's are unitary operators. They can be represented in terms of quantum gates. Now, the Hamiltonian operator also can be transformed and written in terms of unitary operators. So you can also write those in terms of gates. Now, the phi 0 is in terms of single particle states, like a 1s up or a 1s down. Now, each of them is a qubit. So if you think of an electron in the 1s up state, it's either occupied or not occupied. So it can have two possible states, one corresponding to it being occupied, the other not occupied. So that's like a qubit. So a single particle wave function, okay, or an orbital is like a qubit. So those are the qubits. So you see what we have, the energy expression we have in terms of qubits and quantum gates. So you can construct a quantum circuit to calculate the energy. That will consist of qubits and quantum gates. And then you can do the operations and get a result using a quantum computer. So this is an example of how a quantum mechanical quantity can be calculated using a quantum computer. Now, remember, the choice of u is not unique. So you can choose u in a very clever way to get both accurate results and results that are fast. You're looking for speed and you're looking for accuracy. And u allows you to do that. Now, u depends on a parameter theta. Like you remember that we had the rotation grade depending on theta. So you can vary theta till the energy E0 is minimized. And that would be the variational principle, using the Rayleigh-Ritz variation principle, and using theta as your parameter, you can calculate the energy variationally, you see. So now this is the variational quantum eigensolver, which is one of the most important quantum algorithms now for near-term quantum computing. Okay. So Dr. Prasanna is going to talk more about that. So let me now conclude my talk. Next slide, please. So I'll conclude by saying that the emerging area of quantum information science and computing is based on the principles of quantum mechanics. The unit of information on a quantum computer is the qubit, as opposed to a bit on the classical computer. Operators which can be represented as quantum gates act on these qubits and can manipulate them. Qubits and gates are used to build quantum circuits, which are used to carry out complex operations required by an algorithm. Okay. Now, the phenomenon of superposition, especially quantum entanglement, which a quantum computer makes use of, can lead to significant speed up in some very important problems, including atomic and molecular calculations. Now, there have been 2 landmark papers which have achieved quantum supremacy. Now, the VQE algorithm that I talked about for calculating the energy of an atom, it's part classical and part quantum, because the classical part was for obtaining the single particle wave function. So the qubit calculation was done on a classical computation, but the energy was on a quantum was using a quantum computer. Now, the VQE calculations, I just gave an example of the energy of an atom, the grand state energy. So that can be applied for any quantum many-body system in principle. And that is likely to find applications in drug design and for new materials. Now, I mentioned about quantum annealing. That's a promising route for optimization problems and can be applied to both scientific and social problems. Now, finally, I would like to say that important hardware and software advances are being made and are also expected in superconducting, trapped ion, ultra-cold atoms, photonic, and silicon quantum dot qubits in the future. Thank you very much.
Thank you, Professor Das, for this excellent talk. So after, I had done my PhD with him and also collaborating for a long time, but still whenever I hear a talk from him, I learn something very new. There are questions, few questions in like WebEx itself, and also there are some questions in YouTube. And I also see that audience, they ask questions, and some audience there response to them. So we have both type of people, and here we have only 5 minutes left for the next talk. So we'll take only a couple of selective questions. And if you have more questions, then maybe in the end of the all the talks, like we'll again discuss some of the talk questions that cannot be answered right now. So let me read out first question, that is from Mr. Yaswant Acharya. So he's asking that is it possible to compare quantum computer with classical computer in terms of complexity, size, and power?
I think it is problem dependent. In general, I probably think it's not possible, but for a specific problem, like, factorization, like finding the prime factors, I think one can compare, and there quantum computers will do better because of, Shor's algorithm. And the example that I considered, that is the calculation, the ground state energy, at the moment, classical computers can do better. Okay. But as I told you, with a suitable choice of quantum gates and qubits, maybe there is a possibility, and of course, a suitable algorithm also, like VQE, that a quantum computer can do better than a classical computer. So there are some selected problems for which a quantum computer is better or potentially better. But I don't think one can generalize and say that quantum computer is better than a classical computer for all problems.
Yeah, so Mr. Baravalia, he wants to know whether you can give some more information about silicon quantum dots.
Well,
can you give some more information about silicon quantum dots?
Yeah, I mean, the silicon quantum dots, these are basically, the qubits are like the spin, I mean, you take, so there the qubits are the spins, up and down spins. And the advantage is that you don't need very low temperatures for that. And it is scalable, I mean, that's an advantage. And the disadvantage is that you can't keep the qubits entangled for a very long time, because any disturbance can disentangle those. So the decoherence time is not very long. Okay. Now, I would say that one could Google and look up some good review articles on this, or go to the website of the Australian group, which is led by Michelle Simmons, Simmons, and one can get a lot of information about silicon qubit, silicon quantum dot qubits from Michelle Simmons' group in Australia.
Okay, the same person also wants to know whether we can invent quantum programming like C, Java, Python, or something like that for quantum using qubits.
Oh, well, yes. I think that's an important area. So my last point in my conclusions was that important developments in hardware and software using different qubit platforms are taking place and will take place. This is one of the things I had in mind. I mean, people are actually, quantum software is a very, very important area. And people are developing quantum software depending on the hardware, the quantum hardware. And that's a very active area of research. And there are many startup companies that are very actively engaged in this. For example, there's a company called CQC, Cambridge Quantum Computing, and many companies in Canada, startup companies, all over the world, China, US, they're working on this aspect. And a lot of people, they're now talking about, standardizing it. That is, just as Unix is something which standardized the operating system for classical computers, people are thinking about standardizing, quantum operating systems also. So yes, this is a very active area of research, and there's a lot more that can be done.
Okay, thank you, Professor Das. So there are many more questions, but I think some of these questions also will be answered by the, in the second talk. So I'm not reading them out. So thank you very much. So we'll now move for the second talk, and the talk will be given by Dr. Srinivas Prasanna. He is again from TCG Crest, Calcutta. Yeah, so his background is actually he's from BTech in mechanical engineering and from Shastra University. He completed that in 2010. Then he joined, for this integrated MSc program, PhD program in IAEA. That time it was, it started. And so he completed a PhD, MSc, as well as he also did his PhD there under the supervision of Professor BP Das again. But Professor Das had left this place, so Professor almost had worked this, he did his PhD almost independently. And after that, he had done his first postdoc in IAEA. Then he was also a postdoc here at PRL for 2 years. And he was awarded Best Thesis Award by ISAM in 2019. And recently he has joined as an assistant professor at TCG Crest to carry out this kind of quantum computation for using many-body methods. So now it's up to you, Dr. Prasanna. So please share your slides and present your talk.
Okay. Okay, I've just started sharing my screen. My screen is not visible still, right?
Yeah, Bhusit, I think you have to stop sharing your.
Okay. So is my screen visible?
Yeah, go ahead.
Okay, thanks. So hello everyone, and thank you to the organizers for giving me an opportunity to present this talk about our recent work in this conference. And thank you, Professor Sahu, for your very nice introduction. So this is the title of the talk today. It's a rather long title, but then we'll start looking at each part of the title, each of the terms in the title, and then we'll try to understand what we have done here. So this is our first work on quantum computing from our group. Our background is quantum many-body theory of atoms and molecules. So our work by its very nature is very compute intensive. So there were times when we have even run our jobs for months. So like Professor Das said, when quantum computation offers a promise of tremendous speed up, then it's really exciting. So this was a great opportunity for us to start working on these kind of problems, but now within the framework of quantum computation and simulation. So this work was done with Sumit, who was an internship student at PRL and now is an internship student at Secure. and then me, of course. And then we started this work with Professor Sahu when I was doing my postdoc with him. And Professor Das, who gave the previous talk, he's also a part of this work. So the four of us have done this work, and we have recently submitted this work. We are also working on other problems, and these are our collaborators, Professor Debashish Mukherjee, who's now with Secure, Professor Sugisaki, whom Professor Das was mentioning about, who's from Osaka City University in Japan, Dr. Rahul from IIT Bombay, and his two students. So the title of the talk, so we'll start looking at what the title tells us. So basically we calculate ground state energies of some atomic systems. So that's the atomic systems part. And then what we basically are interested in doing is assessing the precision of certain many body effects. Particularly they refer to electron correlation effects, which we will look at in detail when we go to the talk. So this sounds a lot like traditional atomic or molecular physics kind of a title, except that now we don't do it on an HPC on a classical computer, but instead we do it in the framework of a quantum simulation. The algorithm we use is a classical quantum hybrid called the VQE algorithm that Professor Das introduced in his talk. So the outline will basically have us looking at quantum many-body theory first, because at the end of the day, we want to do atomic calculations, and atoms have many electrons. So this very much becomes quantum many-body theory. Then we look at the VQE algorithm very briefly. And then we'll connect these two seemingly unrelated topics, and then see how we can calculate atomic energies using the VQE algorithm. In the last part of the talk, I'll very quickly go through the results and then conclude and also talk about ongoing and future works in our group. So we'll begin with quantum many-body theory. So for any property that we want to calculate, say for some application on a quantum mechanical system, be it an atom or a molecule or a solid, then what we would really like to solve is the Schrodinger's equation. It's an eigenvalue equation that looks like this. H psi is E psi. H is the Hamiltonian that describes the system. Here for an atom, the Hamiltonian looks like this. So you have the kinetic energy term and the potential energy terms. You don't have the familiar looking Planck's constant and mass of the electron, because we have written this down in atomic units. But this is basically the kinetic energy of each of the electrons summed over all of the electrons. So this is your familiar p square over 2m in disguise. These two are basically Coulombic interaction. So this is the electron nucleus interaction, and this is the electron-electron interaction. Both of them are just Coulomb potentials, right? And then psi is the wave function of the system, and this is what we are really interested in. Why? Because once we calculate the, once we get the wave function of the system by solving the Schrodinger equation, we obtain any property that we want by just evaluating an expectation value expression that looks like this. So this is the bracket notation that Professor Das already introduced in his lecture. So I'll just use this notation freely here. One note that I made in between is that instead of writing the Hamiltonian this way, in the more familiar and intuitive way, we write it in a rather different way. And this is what most of the people who do quantum many-body theory adopt. This is the second quantized notation, where we recast the Hamiltonian in terms of these fermionic creation and annihilation operators. It's summed over PQ here. So this first term is basically nothing but these two terms written in the second quantized form. And the second term in this second quantized Hamiltonian is this term, 1 over Rij term here. So HPQ is just a number. It involves, it's an integral, and it involves the two spin orbitals, so the two single particle wave functions whose indices are denoted by P and Q, as well as these operators, and these are creation annihilation operators. Similarly, this is also an integral. It's also a number, therefore. It has 4 indices denoting 4 single particle wave functions or 4 spin orbitals, and it involves the 1 over Rij operator, and then you have these creation annihilation, fermionic creation annihilation operators. So although it may sound a bit difficult for those who are not accustomed to second quantization, we'll see that this really becomes very convenient to work with. It allows us to do manipulations and calculations very easily. So often one uses this kind of a notation. Later in the talk, we will also see that we can write down parts of the wave function in terms of the same second quantized notation. So this is the overview. So we want to solve the Schrodinger equation, get the wave function, and get a property, whatever property we want to calculate by evaluating an expectation value. But the problem is that only for the simpler systems like hydrogen or H2 plus molecule, we have exact solutions. So you go anywhere beyond these two very simple systems, then we don't have an exact solution for the Schrodinger equation. Therefore, what one does routinely is go for approximate methods. I mean, that's the only way you can really obtain the wave function, because you don't have any exact solution. And we will look at 3 approximate methods, and our starting point would be the Hartree-Fock theory, which Professor Das again introduced as being a mean field approach. So instead of basically treating the electron-electron interaction like this, where two electrons interact in a pairwise fashion with the Coulomb potential. In the mean field approach, every electron actually experiences a potential that is an average potential, average load potential of the remaining n-1 electrons in that system. So it is in that sense that this becomes a starting point, and it is for that reason that it's called a mean field theory. But this becomes a very good starting point for most of the theories that we build to calculate the wave functions more accurately. The Hartree-Fock wave function itself is calculated by solving a complicated integral differential equation. In practice, we solve it by recasting it in its matrix formalism, and then we choose an appropriate single particle basis set, and then we solve the Hartree-Fock equations. Now, like we saw earlier, Hartree-Fock is only a mean field theory. It does not really capture electron-electron interaction in the pairwise Coulombic way that we would expect it to. So whatever physical effects lie beyond the Hartree-Fock theory, those come under the umbrella of electron correlation effects. So whatever is beyond Hartree-Fock, we call it electron correlation. Some examples of theories that capture electron correlation are many-body perturbation theory, which is basically the familiar perturbation theory from coursework, but of course much more sophisticated and to suit the many-body system of interest to us. Configuration interaction, or CI, is simply where you diagonalize your Hamiltonian in a suitable n-particle basis. And couple cluster method is something that we'll see in a lot of detail in the coming slide. So we'll now start with the couple cluster method. It's called the gold standard of electronic structure calculations, and it has earned this title because it gives really accurate results. It's known to provide excellent results for so many systems. But the wave function itself is written this way. So you first start off with the Hartree-Fock state, and then it is acted upon by this kind of a non-unitary E par T sort of an operator, where T has n terms, T1 plus T2 all the way up to Tn for an n electron system. What each of these terms are and how an exponential structure arises can be seen by looking at this diagram. So here, let's choose the beryllium atom as an example. It has 4 electrons. So I've just drawn 4 circles representing 4 electrons. Now we are interested in going beyond the Hartree-Fock approximation. So you can think of this as the Hartree-Fock state. And you want to really capture the electron-electron interactions in real space, which is basically recast as virtual excitations in orbital space. So all of this is done in orbital space. So you take into account each of these electrons being excited to some unoccupied orbital. And then there are those many unoccupied orbitals available to you as you've chosen your single particle basis. So if you look at the mathematical form, it's exactly this that T1 denotes in a mathematical way. Here, the second quantized notation is a bit more friendly. It tells you that an occupied spin orbital I has been annihilated and A has been created. And then you have to take into account all possible such what are called one particle, one hole excitations. But then you would expect each of them to have a different weight factor. So this T amplitude basically denotes that particular weight factor. And then you extend the same to two particle, two hole excitations, where two such occupied spin orbitals are excited to their unoccupied counterparts. And then you have to sum over all IJAB, where IJ referred to these two occupied spin orbitals, and AB refer to the occupants. And then there's a weight factor TIJAB associated with this. So again, when you say you sum over, it means you take into account all possible such two particle, two hole excitations. Now you also can have two one particle, one hole excitations, but happening independently. That means you don't have a single weight factor governing these. You have two excitations that look like T1 with two different weight factors. So that's called T1 square. And now the idea is to ensure that we are able to count, and of course, while taking care not to overcount all such possible particle hole excitations arising out of your reference state, which in our case is the Hartree-Fock wave function. And once you do this, and once you account for overcounting, you will see that an exponential structure naturally arises. So this is basically how couple cluster theory accounts for electron correlation effects. And for solving for the unknown T amplitudes, or these weight factors, we solve what are called the couple cluster equations. Like Professor Das said, when you work with quantum computing, you would want to work with unitary operators. So here we choose to work with a unitary version of the couple cluster theory. It's called the unitary couple cluster method, where E par T is simply replaced by E par T minus T dagger. And then this ensures that this operator is now unitary. So here a unitary operator acts upon phi naught. And this accounts for all the electron correlations. This is how you calculate your wave function, and then you get your property. Okay. Now we'll also take a very quick look at configuration interaction. Basically, like I said earlier, what we do is you take the Hamiltonian and you diagonalize it in a suitably chosen n-particle basis. So by an n-particle basis, what I mean is the Hartree-Fock state, the Slater determinant itself, and then all of the single excitations or double excitations and so on that are possible out of the Slater determinant, but within a suitably chosen single particle basis. So this is how you describe psi here. And then when you put put this into the equation and then see what you get. You get a matrix equation that looks like HC is EC. And now your job is to just diagonalize this Hamiltonian. Now, if you're going to take into account all possible n electron basis functions that arise out of your single particle basis. So as an example, let's go back to the familiar beryllium. So beryllium atom has 4 electrons. Let us assume that we choose a small basis set, single particle basis set that has 10 functions. So now 4 of those go to your occupied spin orbitals, and then you have 6 of those that are unoccupied. So it is only those many excitations that you can then generate, those many such Slater determinants that you can generate. And then if you're going to take into account all of those, the resulting CI equations that you solve is what's going to give you full CI. And the reason why we do this is because this is the best result that you can get within a given single particle basis. So in other words, after we carry out our calculations of atomic energies in a VQE algorithm, we need something to compare it with respect to, right? We need to compare our results with something that can serve as a reference. And there, FCI results happen to be an excellent point.
Prasanna, can you just please hold on for a second?
Okay.
Somehow we are not able to see your screen. Prasanna.
Oh, I see. Okay. Are you able to hear me?
Yeah, we can hear you, but I can see, but in YouTube, they are not able to see. Can you again change the share mode option?
Yeah, can you please unshare and share again?
Okay. I don't know how to unshare this. So
how to share them?
It allowed me to share, but it didn't allow me to unshare. I don't know how to unshare this.
Because probably you are sharing a file, not a presentation. That is the problem.
I see. What about now? Is the first slide visible?
We can see, but not in the YouTube.
Okay.
See, WebEx we can see, but not in YouTube. So probably if you are sharing it as presentation, then it can go, but not a file.
Okay. I see. Now? Is a PDF file visible now?
Yes.
Visible in WebEx, but let me see if it is visible in YouTube as well.
I think, Bhushit, I had the same problem. So I was not able to share the talk. I was able to share the file. I think that option was not shown.
Yeah, but that option is now.
I see. Now I'm not even sure how to unshare this.
Okay, let us proceed, and maybe you'll see. Again, you can, okay, you just continue. So for the next talk, we'll see.
Okay, but
yeah,
okay.
Now I have unshared your
Okay.
now presentation in PDF file. Or
yeah. I have my presentation in a PDF file.
Yeah. So can you just go to that, open the PDF file, go to share.
Now we can see actually, Prasanna, now we can see the PDF file in YouTube.
Oh, I see.
Yeah.
Okay. I see. So
you share in the same way you did for.
Okay, sure. So now the outline of the talk is visible, right? I'm on that slide currently.
On WebEx, let me check on YouTube.
Okay.
Yes, it is visible. Yeah.
Oh, it's visible. Okay.
Yeah. Please go ahead. Yes.
Okay. Sorry about this. Okay. Okay. So to summarize till this point, because with this we'll complete our summary of quantum anyibody theory. We want to solve the Schrodinger equation, but because there's no exact solution, we use approximate methods. We want to get the wave function and therefore calculate properties. And then we saw 3 quantum anyibody methods. We saw the Hartree-Fock approach, we saw couple cluster, and then we saw configuration interaction. And we saw that what's called full configuration interaction, or FCI, that gives the best results that you can compare with. Now we'll go to the VQE algorithm. So again, like we saw in the previous talk, quantum computing does offer a promise of speed up for certain problems. And when you choose a problem, and then when you get a speed up on a quantum algorithm as opposed to a classical one, and when you can actually demonstrate it, it's called quantum advantage or quantum supremacy. Again, Professor Das gave a couple of examples of quantum advantage being achieved. Now we will move on to the question of whether we can think of such a quantum advantage for problems where we want to solve for atomic and molecular systems or their properties. So the quantum algorithm that one uses for it, and which promises a super polynomial speedup, is what's called the phase estimation algorithm. But this is not what we are going to see today because of this part of the sentence, which says it's for the future. The reason is that it ends up taking up a lot of gates. You need a lot of qubits. And since we live in the NISQ era, where we are severely limited by the number of qubits and limited by the errors that we can have on actual hardware, phase estimation is not really the algorithm to go to. So that's why people opt for, more and more people are now opting for the VQE algorithm, which is not a pure quantum one, but it's a classical quantum hybrid, where you choose parts of the algorithm to be performed on classical computer, and then parts of the algorithm are performed on a quantum computer. And the reason why you call it variational is because it relies upon the variational principle. I'll explain what that means by just looking at the expression for energy. So it's just psi h psi over psi psi. This is familiar to you already, except that I now parameterize the wave function with a set of parameters theta. I'll explain that in the next slide. And now, because your wave function has to be represented by a unitary operator acting on a reference, you just get this. And the energy that you thus calculate inside this sort of a framework is guaranteed to be an upper bound to your actual ground state energy. So that's the advantage that a variational approach really offers to us. And in this case, for psi, we are going to choose not the couple cluster method, but the unitary version of the couple cluster method. So the UCC method is what we are going to adopt here, and it satisfies the variational principle. So now we look at the VQE algorithm in a little bit more detail, besides just telling that it's a classical quantum hybrid and it's a very useful algorithm. So we'll again get back to this expression that we wrote here. So we saw in the very first slide that the Hamiltonian is often represented in second quantized notation in terms of creation and annihilation operators. We also saw in the slide where we introduced couple cluster method that here too we adopt a second quantized formalism. Now we want to go from these second quantized operators to gates so that you can put them in circuits and then you can evaluate these circuits, right? So you need to do some sort of a mapping that takes you from these sort of operators, second quantized creation annihilation operators, to a qubit form. One such map is called the Jordan-Wigner transform. I'll not be getting into the details of any of these maps here, but you just need to know that it's not unique, and a very simple map is the Jordan-Wigner transformation. I've just chosen this as an example. So if we take a very small molecule, which is just the H2 molecule, and we choose what's called the STO3G basis. Again, the details don't matter, but it's a very small basis set. It's just that much that really matters here. And it's so small that it allows you to do all this calculation with just 4 qubits, right? So if you take the Hamiltonian, and if you're going to take a look at one of those mapped terms, one of those transformed terms, then it looks like this. There's this number small h, and then there's an x0, x1, y2, and y3. These 4 matrices are in their tensor product. This h is actually the number that we saw much earlier as integral. So an appropriate HPQRS kind of an integral will actually come here. And there will also be a multiplicative factor along with it because you have converted second quantized operators to their qubit form. So that's basically all this is. But then the question is, where do we get this from, right? So this is where the classical computing part of the VQE algorithm first comes in. So on a classical computer, you first do the Hartree-Fock calculations. Once you do the Hartree-Fock calculations, you can calculate those integrals, HPQ and HPQRS that we saw. Once you have these numbers, once you choose a particular mapping scheme, and then you're able to map your Hamiltonian in qubit form, then you can start constructing, and you can start evaluating the expression for E theta. So the state itself will look like 0011 when you Jordan-Wigner transform it. What it means is something like this. So like Professor Das said, if a spin orbital is occupied, then you give it 1. If it's not, you just assign a 0 to it. So here, H2 molecule has 2 of these electrons. These are the 2 spin orbitals. And there are 2 other slots for the spin orbitals to get excited to, which is why you have 4 qubits. And this 1 is simply denoted by this sort of a circuit, because an X gate basically flips your qubit. You initialize with all zeros, and then this gives you a 0011 in the ket notation. Now, the part of U theta that describes the double excitation that we are interested in is basically this. And this sort of a complicated looking exponential structure, which ideally would expect would have infinite terms, is very compactly put into just this circuitry. So you just have 3 2-qubit gates. there are 3 other 2-qubit gates, and then there's a single qubit gate. So what you would ideally expect to be a very complicated kind of an expression for U, because it's an exponential and all that, is simply compactly put within the framework of 7 gates acting on these 4 qubits. The only thing that I didn't explain here is what this parameter here is. This is a rotation gate, which means it does rotation about some axis on the Bloch sphere by some angle. And that angle is what this theta denotes. And if you have to connect this theta back to the couple cluster equations, then this theta is the T amplitudes basically play the role of this theta. So these are unknowns. You want to really evaluate those set of thetas that gives you an energy, but not just any energy, because we work within a variational framework. You want to make sure that you get the minimum of that energy for those set of values theta. So therefore, to recap, you begin on a classical computer, you do Hartree-Fock calculations and obtain your relevant integrals. These would serve as multiplicative factors later once you're able to evaluate this expectation value. You have an appropriate mapping scheme, and then you evaluate this in a circuit form. The initial set of thetas had to be put in as guesses. So you have a set of guess parameters theta. So let us say you have 3 thetas in H2 molecule. Those 3 have to be, 3 guess values have to be supplied inside. E theta is then calculated, evaluated using these circuits, and then it is passed on back to a classical computer where it is sent to an optimizer. This optimizer will do the job of updating theta in such a way that the energy reduces further. And once these thetas are updated, the updated parameters are sent back here. So these would serve as the new values of theta for you to evaluate the circuit again. And this keeps going until you're able to get your ground state energy in a minimum. So till a minimum is identified, this process goes on. Now, the different things that go into this kind of a calculation, or the different knobs of a VQ algorithm, so to speak, are first your choice of basis, right? You want to choose a particular single particle basis. In our work, we have chosen 4 very small basis sets. Again, we choose very small. When I say small, I mean small with respect to those that one is accustomed to in standard atomic and molecular calculations. For example, these 2 basis sets you see here will only lead to 10 qubits. The bottom 2 will only lead you to 18 qubits, but even 18 qubits is considered very expensive in the current era that we live in. So in that sense, we are choosing small basis sets, which is why we can't compare the energies that we obtain using VQE algorithm with experiment, but rather we should compare it with the best energy that one can obtain within that basis. So that is where your FCI energy really becomes useful. The variational form, or what you choose for U theta, which if you recall, Professor Das said that it's not unique. So in this case, we just fix it to the UCCSD variational form. So this form is fixed. And then what choice of mapping do we go for? That is, what sort of a scheme do we employ to go from the second quantized operators to tensor products of polystrings, which can be implemented as gates. So there are 3 such mapping schemes that we have chosen in this work. What about the simulator itself? So we are not doing a quantum computation in the sense of working on a quantum computer in this work. This is a pilot study and this is our first work. So we have worked in the framework of a simulator. And simulator also gives you the advantage of not having to deal with errors that a real quantum computer would really give you. But still, the simulator itself can give you 2 options, right? One is where you can just do your standard matrix manipulation. So the algorithm is still classical quantum hybrid, but you don't have to necessarily conduct measurements here. So you can just do matrix operations and still get your results. That approach, you say, uses the state vector simulator. The other is to go for the standard measurement based approach, which is called the QUASM simulator. So we used both these simulators. We have used these 3 mapping schemes and we choose 4 single particle basis sets. In all, we look at all these combinations, we look at our results, and then we want to see how good the results are really.
May I request you to wind up the talk in another 5 minutes or so?
Sure, yes. So this is basically the problem statement. The optimizer we choose is Kobila. It is known to be a good optimizer in literature, but we could have really gone for any other optimizer that gives reasonably good results. But this is time tested. The systems we choose are really small systems again, beryllium, lithium minus, and boron plus. Again, because we are in the NISQ era, we are limited by the size of the system that we can work with. Finally, we compare our results with Hartree-Fock, UCC, CC, and FCI. The reason why we compare with Hartree-Fock is because this is exactly what allows us to assess how precisely we have captured electron correlation effects. So with this, our survey of VQE and the problem statement finishes. I'll not focus too much on the results because then that would become quite technical, but I'll only give the final take-home kind of stuff from this work. The first thing is that most of the works work within a state vector simulator, which means even though you work with a classical quantum hybrid algorithm, this expression itself is not evaluated using measurements, but just by doing matrix operations. But here we decided to go for a departure, partly also because this is a natural transition to a quantum computer, right? I mean, on a real quantum computing device, you are going to carry out measurements after constructing circuits. But the problem that we have here is because it's measurement based, each time you carry out a calculation, you are not guaranteed to get the same result. Also, you need to repeat an experiment many, many times. So the number of times you repeat an entire VQE procedure, that's called the number of shots. And then each time when you fix the number of shots and repeat your calculations, you're going to get a huge spread in your results. And as expected, as you increase the number of shots, the error due to your statistics will reduce, and then the maximum and minimum in this graph also reduces drastically. So your mean value is fairly accurate. These horizontal lines basically represent all the classical computing results, Hartree-Fock, UCCSD, CCSD, and FCI. As you can see, these results are very, very close to UCCSD. So this is just one example of the challenge that one would face when they work with QUASM simulator, but which will, of course, allow us to naturally transition to working on a quantum computer. So here I've just chosen the results for one system, beryllium. I'll skip discussing the graph, but I would rather discuss what the graphs tell us in the conclusion directly. So when you use the state vector simulator, you do get excellent results because you're directly doing matrix operations. You're not limited by statistics. So the kind of accuracy you get is within millihartree. Hartree is the atomic units of energy, and millihartree is considered to be chemical accuracy. And this is with FCA that you get this kind of difference, and it's almost independent of the mappings. However, with a more realistic and more futuristic outlook, if we use QUASM, then we do incur errors of tens of millihartrees. So here the scope for improvement. We did identify that one of the basis sets which uses 18 qubits is really not that good, and a 10 qubit basis set would still do. So that opens up new avenues for our research. And our work is very timely and relevant. Why? Because like Professor Das again said, IBM has announced that they will release what's called IBM Quantum Condor, which would have 1000 qubits. And there, basically, we are just going to scale up these calculations. Whatever we learn from these calculations, we are going to just scale those calculations up there. And this pilot study will really pave the way to extend our calculations for not just heavier atomic systems, but also for other properties. I'll wind up by very briefly talking about ongoing and future works. So like Professor Das again mentioned, with Nakamura's group in RIKEN, we are working on an actual quantum computer, a superconducting platform. We are trying to get the ground state energy of lithium as well as the hyperfine structure constants. We fixed the ansatz to the unitary couple cluster ansatz, so we could have used any U theta in principle. So we are also working on a domain of ansatz called the hardware efficient ansatz. Now, we cannot just get energies, but we can also try to calculate ionization energies. We can look for other properties. We can transition to real quantum computers by studying how noise models would behave. We can look for different error mitigation schemes. And although this is for the future, it is still good to study quantum phase estimation because of certain advantages that they offer for spin adapted formalisms. And lastly, a work that we very recently just began is applying quantum computing to fluid dynamics. So with this, I'll thank you for your attention, and I'll stop. Thank you.
Thank you, Prasanna, for this excellent talk. So there are a couple of questions. I would like to request all the participants to prepare the tea and bring it on your table, because we don't have much time for tea break. So in the meantime, let us discuss a couple of questions that the audience have asked. So there is a question by Mr. Soumyaranjan Jhankar. He's asking, what happens if CI Hamiltonian, CI means configuration interaction Hamiltonian, is non-Hermitian? I mean to say, if the system is dissipative in nature, then whether the VQE algorithm works or not.
I think there has been work in the literature. I've seen papers on arXiv where they do treat dissipative systems or open systems, but I'm not familiar with how they treat it. But yes, works do exist on open systems and systems where dissipation is clearly involved in this framework.
There is another question by Mr. Yas Baravelia, who is asking that whether quantum simulator is same as classical computer simulator or something else.
By a quantum simulator, what we do is we run a quantum algorithm. We do things as if we would do on a quantum computer, but then the calculations themselves are done on a classical computer. For example, this circuit can be implemented with real quantum gates on a quantum computer, or you can simply represent these on a classical computer and still do your calculation. So in that sense, you're departing from classical calculations. This is a quantum algorithm. This does involve quantum gates, but then all the calculations are carried out on a classical computer instead. So this is basically an example of what's called digital quantum simulation.
He also wants to know if the value of energy for atoms other than hydrogen is not exact, then is it nearly true or is it not true?
I mean, at the end of the day, we can tell this only by comparing with what experiment tells us. The best we can do, if we have to stick only within theory, is
so
to
the
compare
answer
it
is
with the
not
FCA.
exact. it is more, it's approximate, but how, much, it compares with the experimental value. Yeah, so I think with this, thank you very much for this, very nice presentation. And maybe if there are some more questions, I will come up in the end of the, all the presentations. And so now we'll move to, to further this next presentation by Dr. Subhadeep Dey. So, yeah, so Dr. Subhadeep Dey, he did his BSc from Bardhaman University during 1998 to 2001. Then he did his MSc from IIT Kharagpur, and after that he moved to Netherlands, KVI, formerly known as KVI, now it's the University of Groningen. So he did his PhD there on laser cooling and trapping of barium ion. And then after that, he was a post research associate at NIST, Joint Quantum Institute of NIST. And that belongs to actually Professor Phillips group. And then he came back as a scientist. He joined, CSIR as a scientist, and then he worked there, as a senior scientist till 2019. Then he has moved to IUCAA recently, and he's an associate professor there, and he's trying to carry out this precision quantum measurement, like quantum metrology and something like that, like atomic clocks. So with this brief introduction, now let me request Dr. Dey to share the presentation and go ahead.
I'm not able to, now it works. Okay, so thank you, Professor Bijay Sahu, for kind introduction, and thanks to Professor Bharadwaj and Professor R.C. Singh for the invitation and arranging this nice half-a-day workshop kind of thing. So is my screen visible?
Yes, yes, yes.
And do you see the first slide? And I'm going to change something. Do you see the change? Do you see the second slide?
Yes, yes.
Okay, yeah. So let me begin. My title of my talk is Quantum Metrology Using Accurate Clocks, and this is basically we are celebrating the World Quantum Day that was just yesterday, and we are celebrating it today. So the main idea of celebrating the World Quantum Day is basically explaining to the general public about the usefulness of quantum science and technology. So remember, it's for general public, and that's how. And what do we need to explain? Basically, understanding the nature of fundamental level using the quantum science and technology, and developing new quantum technologies, not the classical ones, but quantum technologies, and what could be its societal impact. That's what the general public can be interested on. This is particularly because all of our research are funded by public funded institutes. So it's our duty to tell them what we are doing using their money. So let me begin. With understanding what is metrology means. Metrology is basically making some measurement of a particular quantity using scientific and systematic ways. Now, when we add quantum to that, that means basically we are either using some quantum phenomena to measure something, like for example, let's say squeeze light or superposition or entanglement, something like that. Or it could be like we are doing some experiment to prove some quantum hypothesis. Or it could be like, let's say, some very, very ultra sensitive measurements, which we call precision measurements in atomic physics, and which is beyond the classical limit. So it can be only done in quantum level. So these are basically the wide aspects which covers the quantum metrology. And let me give just one simple example before I actually start my actual work. So here you see the picture, which is Giravali Observatory, which belongs to IUCAA, and that is top of a hill, like 60 kilometers from Pune. And you see this road, which is going like circulating through the hill and going at the top, and this is the observatory. And so this part of the road and where the observatory is located, it's like a couple of meters difference in height. So we can use some classical techniques, some leveling techniques to measure what is the height difference between this part of the road and where the observatory is located. But that would be classical things. We would not be able to do it very, very accurately. But using the accurate clocks, and what I mean is like ultra high accurate clocks, we can actually measure this height difference with an accuracy of less than a centimeter. And that kind of sensitive measurements once we do, which is beyond any classical scope, is part of the quantum metrology. And there are many more such kind of things. And I will take just probably one example during my talk. So my talk is arranged in such a way that first, like let's say 50% of the talk is in really very basic level so that everyone can understand. Then I would say what we plan to do at IUCAA very briefly also. I would try to keep it at very basic level. So being a physicist, what we do, we try to basically understand all our natural and physical phenomena using some models. And most of the things we basically try to understand through classical models, classical pictures, but there are many things which cannot be understood through the the classical models. Then we have to take the help of quantum models. And still there are many things which cannot be actually explained by quantum physics. Like these are the future scope, like gravity cannot be explained by quantum physics, or the existence of dark matter and dark energy, and so on, so on. So even though quantum physics is like covering majority of what we understand, what we believe basically, but still there are several open questions which cannot be understood through the quantum mechanics. And that's how the other models, like let's say string theory or membrane theory, those kind of things comes into the picture. So as Professor Bhanudas was saying in his lecture that we are going to the second quantum revolution, the quantum physics actually, the conceptualization came in early 1800, but the real beginning was with Max Planck in year 1900. And the name quantum mechanics was introduced by Max Born after 24 years. And now we are in 2021, so it's approximately 120 years we have traveled through the quantum mechanics. And what it gave, starting from the foundation of the quantum mechanics, like let's say several things like quantization of the energies, which was told by Planck, and then uncertainty principle, and like particle have a wave nature, wave particle duality, and so on, so on. Many quantum effects were discovered, like Einstein's photoelectric effect, and so on. Then quantum field theory was formulated, and different, like our particle physics model was explained through quantum mechanics, like quantum electrodynamics, quantum chromodynamics, quantum fluid dynamics, and these are all part of the standard model of particle physics. But yet that doesn't include the gravity, which is an open thing yet. And now we are in an era of using this quantum mechanics knowledge to build technologies. Yeah, so like from foundations, we did many things in between in last 120 years. One of them I'm just citing here, like realization of the Bose-Einstein condensation, even though that Boson statistics was given much earlier, but realization came only in early 1990s. And fermion degeneracy was experimentally realized a few years later of that. And now we are in an era of using this kind of techniques to build instruments, to build machines. For example, quantum computer or quantum simulator using trapped ions or neutral atoms or spin qubits and so on, so on. There are different platforms. The atomic interferometer, atoms also have a wave nature. So as the wave produce the interference pattern, so atom can also produce the interference pattern, and that will have much more controllability, because atoms can be laser cooled and trapped, so it can give much precise results compared to photon interferometers, even though LIGO is there, which is a photonic interferometer. But it's very difficult to build. Rather, the atomic interferometer can be really, really compact and small in size. Then we can prepare the clocks using the quantum phenomena and quantum logic phenomena, which I'm going to talk a little bit in my talk, and of course quantum communication. So we are in this era right now, and it's an actually upcoming field. So there will be many technologies which will be coming in next few years or decades or centuries and so on. And in future will basically live in the quantum domain, most likely. So our daily life will be using quantum phenomena. So in last 120 years, as the quantum mechanics was developed, also together with that, clock also evolved from less precise clocks to very highly precise clocks. And what you see here in the picture in this plot, so the x-axis, it's actually 700 years I'm plotting, and then this light red band shows about 120 years, and the vertical axis shows the duration of the clock that operates to give 1 second inaccuracy. So you see, like, let's say in year 1900, when the quantum mechanics was first formulated properly, that was an era of pendulum clock, and that was kind of accurate to 1 second over something like in 1 year time scale. And now we are living in an era where the atomic clocks, the best atomic clock, is accurate to 1 second over 35 billion years. Remember, 13.8 billion years is age of our universe. So it's much more than basically we have lived, or basically the universe was originated. So it's kind of that kind of precision level or ultra sensitive level what we are talking about by these quantum measurements and so on. So let me give you what is the problem with the pendulum clock. So this is a picture, like, sorry, short video from the song from a movie Kiamat Se Kiamat Tak, and you see there are pendulum clocks and they are not synchronized. They are oscillating at a different rate. And the reason is, even you try to produce exactly same pendulums using the same mechanism, same material by the same person, it is impossible to create identical pendulums, right? Because it's manufactured by some human. It's not a naturally occurring thing. So never you will be able to make two pendulums which are identical in nature, have identical oscillation periods. That's the problem. And that actually gives the inaccuracy. What we can do with the atomic clocks, atoms are just natural particles. So they are identical in nature wherever you bring them or get them. And that's why atoms can be used as most accurate oscillators. That idea was proposed by Rabi in 1945. That was the time during the Second World War. And at that time, actually, the idea was very important, because at that time, due to the war situation, it was very important to synchronize the radio frequency signals for strategic reasons. And just before 1 year in 1944, he got the Nobel Prize. And 1 year later, he gave the idea that nuclear magnetic resonance can be used to make better clocks than anything else. Like at that time, quartz clock was already known. And the reason the atom can be a very good oscillator, because first of all, the oscillation frequency is very high, like it's 10 to the power 10 to 10 to the power 15 hertz comparison to, like, let's say, few oscillations per second. It can be most stable oscillator and identical in nature wherever you take them in the world or outside of the world. It's a most unperturbed system. The kind of perturbations which could give the slightly different systems from one clock to the other clock, even though if it is made by same atoms, can be also calculated very accurately and can be accounted in the actual operation. It can be tracked and laser cooled, so many of the systematics can reduce to very, very almost negligible level, and that's why it can produce a clock which is accurate to 1 second over 35 billion years compared to any other oscillator clocks like pendulum clocks or quartz clocks. Well, to get this kind of very high accuracy, the transitions which are being used in an atomic clock are actually only quantum mechanically allowed. It can be only explained through quantum theory. For example, here you see in this transition, here you see it's an S to D transition, which is transition between same parity states, which is classically not allowed by Wigner-Eckert theorem, which is in quantum basis of which is based on quantum theory. That transition has some minute probability, and that means this transition can be measured very, very accurately. Line width of the transition is ultra narrow compared to a naturally occurring transition, which is typical line width of, let's say, tens of megahertz. Here it is like much below, like 100 millihertz, even lower than that are also possible in some other transitions. So this is basically starting of using quantum mechanics to build the atomic clock. Now, there are two different type of atomic clocks that we typically mankind have realized. One is at the microwave transition, that is the transition between hyperfine states of an atom, and like typically we know, like cesium clocks, it's a typical name. It could be rubidium clock also. And cesium clocks can be built either at the room temperature atoms, or they can be cooled to almost 0° Kelvin temperature, almost, not exactly 0° Kelvin temperature, and that's called cesium fountain clock. As you see here in the picture, so the y-axis is actually UTC, Universal Coordinated Time, that was initially since 1967, it was basically maintained by atomic clocks, cesium hot atom clocks. And then in 1995, the laser-cooled cesium clocks or fountain clocks came into the picture, and you see how the accuracy became much, I mean, 100 times better. So this is up to here, this point, this is using cesium hot atom clocks, and now we are living in this era where the UTC is maintained by, is defined by cesium fountain clocks, and it's improved by almost a factor of 100. So if we put in terms of fractional accuracy, it's few part in 10 to the power 16, and it's extremely accurate for most of our classical or present days application. So far so good, but still mankind is not happy because there are many exciting things cannot be done using these microwave clocks with their accuracy of 10 to the power minus 16. We need even much better clock than 10 to the power minus 16, and that can be done using optical transitions, ultra narrow line width or highly forbidden optical transition, and that's called optical clock. An optical clock, why it is needed? Because to explore fundamental science, which requires much precise clocks than microwave clocks, and also the future technologies like quantum technologies, they would require much precision, much accurate time stamping than what we need today. So to support all these kind of things, science as well as quantum technology, we have to emphasize on optical clock. And there are two kinds of optical clocks. One is using trapped ions, a single ion trapped in a Paul trap, and the other one is using optical lattice. So that is neutral atoms stored in an optical lattice. And I believe the next speaker, Professor Bindya Arora, will probably touch upon these things in a little more detailed way. So I am skipping those details, technical details here. So the idea of optical clock is excited transition and optical transition, highly forbidden optical transition, and then excited state will have very long natural line width. So at some point it will get de-excited. You measure the fluorescence in a direct or indirect way, and the line width of this transition, that is delta nu, is really narrow, like hundreds of millihertz or even lower than that. Then you can measure basically the central frequency nu0 with the accuracy of minimum as delta nu. Yeah, and there so far mankind have reached an accuracy of 10 to the power minus 19. So few parts in 10 to the power 19 using both trapped ion clocks as well as neutral atom clock, and that's what is transferred to, for layman's language, it's like 1 second inaccuracy over 35 billion years. What can we do with this kind of clocks? Of course, we don't need this kind of clocks for our daily life, like let's say to do anything in our life. So what can we do is, okay, by the way, before we say what can we do with this clock, so what kind of effort have gone to develop this kind of high accuracy clocks can be seen here. These are like year-wise some development of optical clock. It started with idea of Rabi in 1945, and then first cesium atomic clock was demonstrated in the lab, hot atom clocks by Essen and Perry at NPL UK in 1955, and soon after that it was commercialized within 3 years. And that's like typical cesium 5071, I think I remember the number right, clock. And then in 1967 the astronomical definition of time was changed to atomic definition based on the cesium atomic clock. Then laser cooling came into the picture during 80s and 90s because laser was available, and cesium fountain clock using ultra cold cesium atoms was produced. in 93. And then in 1997, the SI definition of second was amended, was based on, at present, it's based on cesium fountain clock. That means the cesium atoms are nearly at rest. Then the optical clock was developed, ion clock as well as lattice clock during 2001 and 2005. And so far in last couple of years, they have reached to their best accuracy of few parts in 10 to the power minus 19. And we expect that in couple of years from now, particularly in 2026 CGPA meeting, maybe the time definition will be changed based on the optical clocks. So that's kind of expectation. Like, you know, like 2 years back, the definition of kilogram was changed based on the watt balance. Similarly, the definition of SI second is expected to be changed in 2026 by using the optical clock. And these, I mean, apart from, there are several people who have contributed to develop atomic clocks, starting from fountain, just normal room temperature atomic clocks to the optical clocks. And these are kind of Nobel Prize, which are directly, indirectly, basically, have gone into this kind of development. Starting from Rabi, because it's basically the spectroscopic technique still we use is developed by Rabi and then further modified by his student Ramsey. Then several others, laser cooling techniques were developed by, actually slowing of atom techniques was developed by Bill Phillips and Cohen Tanuji and Steve Chu. Wineland was getting Nobel Prize for basically ion trapping and ion trap based quantum demonstration of ion trap based quantum computation, which is used in aluminum clock quantum logic detection and so on. The optical clock uses a very novel tool which is called frequency comb, and that and associated techniques which was developed by these three gentlemen, Hunch and Hall and Glover. So you see, like 12 Nobel Prize was given, I mean, their effort are used to build atomic clocks in many different ways. So that's the beauty, or that's the kind of effort is required to make such kind of precision machine development. Now, what can we do with such kind of ultra sensitive clock like 10 to the power minus 19, or even better? People are looking for even better clocks. So basically, we want to test like fundamental things of our knowledge. Like, for example, in our standard model, it's considered that fundamental constants and there are some fundamental symmetries. But there are other theories which says they might not be actually constant because of the existence of dark matter and dark energy. So if we can measure if this is constant or it is non-constant, or what is change of rate of change of things, then that would be an indirect way of proving whether dark matter, dark energy, or let's say detection of dark matter at dark energy in an indirect way, or basically gaining our knowledge further and further compared to what we know at this moment. We can do very ultra sensitive geodetic measurement, like, for example, to begin with, I was giving you the example of very accurate leveling. Then it's proposed, there are some proposed experiment to search dark matter and dark energy directly, and also gravitational wave using ultra sensitive atomic clock arrays in cosmos, in different places in the sky. Of course, the quantum information processing, that if you, when it will be actually used, well, what do I mean by it's already in actually used, but basically what I mean, like at its base level, so that you can transfer data very at a very high rate, then you need a very precision clocks, and that can be only achieved by optical clock. Also, the present radio astronomy and optical astronomy, VLBI, very large baseline array. So it's an array of different telescopes through international different countries. They needs to be connected through optical clocks to get the best result from the data they are acquiring from the sky, and many more. So in particular, in our IUCAA lab, we are developing a trapped ion based optical clock, and Once it is developed, we'll focus on this kind of fundamental aspects of science, like looking into temporal constancy of fundamental constants, or local Lorentz invariance violation, and geodetic measurements. I will come to that in few slides. So I won't have time to go into all different kind of applications, but if time permits, I would like to say about the local Lorentz invariance violation, just to sensitize people who are listening to this talk, particularly the students. So we know what is Lorentz invariance. Yeah, so like that means basically laws of physics are independent of the reference frame. But what if it violates? If violates, then that means it will violate CPT symmetry, which is considered to be a very good symmetry in our present standard model. So if it violates, that means we need an extension of the present standard model. Yeah. So what can we do? How can we do some measurements in two different reference frame? Yeah. So what we have available with us, it's like the rest frame of the universe, that is the cosmic microwave background, which is at a temperature of 2.7 Kelvin, and that's considered as rest frame of the universe. That's not changing over time and everything. And then this is not by the way 2D scale picture, so it's just for demonstration. So, and our Earth is a rotating frame. It's rotating with respect to this CMB rest frame. So if we do some measurements on Earth, but then we are measuring also the same thing on our Earth, so we don't have a two different reference frame. So that won't work very simple in that simple way. So we have to do something in a slightly different way, and that I'm going to demonstrate in my next slide. So assume for now that atomic clock is the frequency, the transition frequency of an atomic clock is dependent on the reference frame. That means it violates the local Lorentz invariance. Then the interaction term, or the Hamiltonian, is basically product. It's a tensor basically. C coefficients. It's a second order tensor coefficients which couples the two different reference frame. It's a C mu nu coefficients. It couples two different reference frame. In this case, basically cosmic microwave background frame, that's the rest frame, and the Earth's own reference frame. And then there is a T matrix element. It's also a second order tensor that depends on the atomic properties. So it depends on which atom you choose to make this clock. So let's say you have two clocks, they have identical in nature, but the only difference is they are oriented differently on Earth. So this is a clock 1 and this is a clock 2, and the tail of this cat is showing their basically direction or the quantization axis. So they have the same exactly, let's say ytterbium ion atomic clock, for example, but the only difference is they are oriented differently. That means the C mu nu coefficient for clock 1 and clock 2 will be different. And over the time, as the Earth rotates with respect to the rest frame, this differential of C mu nu 1 of clock 1 minus C mu nu 2 of clock 2 will change because they are changing differently. And then if we see any change of this differential quantity, that will tell us, okay, there is something which is violating, something which is reference frame dependent. And that experiment was done in PTB. This is the experimental setup. Basically, that's what I explained. And they have two ytterbium ion clock which are quantized in two different directions. So this is the direction of one ion clock, this is the direction of the second ion clock, and they measured over different times as the Earth is rotating. And if they do everything very precisely, so that's how the ultra sensitive measurement comes into the picture. So they have to be sensitive to that level so that they can measure this very minute part of the Hamiltonian. And there, ytterbium actually is one of the best candidate that so far people have found for this kind of measurement, because ytterbium, the F state, or that is actually the octopole transition, what we call, not the transition, it's a property of a state. F state have maximum sensitivity to this to this Hamiltonian. Basically, this T matrix element, which depends on the atomic properties, has the highest value for ytterbium F state. That's why they use this ytterbium ion atomic clock for this purpose, and that result gave the best result compared to any other experiments to find out the local Lorentz invariance. So these local Lorentz invariants have been investigated in many other experiments, including the astronomical experiments, like looking into quasar absorption spectrum, and also looking into again some highly forbidden transition dysphorium atom, and then some calcium ion experiment. But you see, these are like orders of magnitude better compared to astronomical experiments or any other experiment. So these are the different coefficients of the C mu nu tensor, basically projections in XYZ plane. And these are like, this gives the best result so far, but still this is not any measured value of local Lorentz invariance. It's only the sensitivity of their measurement. So basically they call it a null measurement. So they don't have any, they did not identify any violation of local Lorentz invariance, because the present accuracy of ytterbium ion clock, which is 10 to the power minus 19 level, is not enough to do that. So we need even better clock. Or
Subhadip, can you wind up the talk in 5 minutes?
Yeah, sure, I will be finished. Yeah. So even you need a better clock to do this kind of experiment. And now I am in almost last part of my talk at what we are going to do in our lab, PQM lab, Precision and Quantum Measurement Lab, that we have started at IUCAA just before the COVID basically started, and kind of going through in a slow manner because of the situation. So here our goals are quantum metrology on ultra-stable optical reference. We want to do precision measurement to test fundamental science using the trapped ytterbium ion clock, and also want to develop quantum technologies using trapped ion systems, particularly clock-based systems. So I will go a little quicker, fast here. So basically, our aim to do this kind of measurement would be to develop an ultra-stable optical reference source. And that, what I was telling about this hunch and etc., they developed this frequency comb, and that gave equally spaced optical lines. But the problem is, if you just take a frequency comb, they are like oscillating it's just a property of the things. I mean, it's oscillating very slowly, not like this in this animation, but they are not stable. So we need something more, and that more is basically optical clock to stabilize them. Yeah, then only it can be useful, or then only these optical outputs of a frequency comb can be useful, because atomic clock is, or basically the optical atomic clock is the absolute reference. So you take the reference from the optical clock and then stabilize the comb, then you have a very stable reference. And to do that, you need some more peripheral technologies, that is some microwave clock also, and some ultra stable Fabry-Perot cavity system. That's an external stability, which gives stability of the systems, external Fabry-Perot cavity, optical resonator basically. So we have to, there are few things which are commercially available that we can use, for example, the microwave clocks and the frequency comb, optical frequency comb, but the major part, that is the optical clock and this ultra stable laser cavity, that we have to indigenously develop ourselves. And then once you have this stable optical reference, you have to develop a technique to disseminate these photons to farthest distance, to thousands of kilometers away basically, to make them usefulness, to compare them at two different locations. And that called fiber phase noise stabilization technique. That's also we have to develop ourselves. That's not commercially available. Then once we have that kind of ultra stable optical photons, it can be used for quantum metrology or ultra sensitive measurements. I'm not reading, I already told you what can be done, so I'm not reading them once again. So with this, I'm concluding. So basically, aim of our precision quantum measurement lab at IUCAA is we want to develop this reference optical clock. In this case, we will be using ions, and particularly our aim to use them is for quantum metrology and developing quantum enhanced technologies. Then our neighbor at IISER Pune, Dr. Umakant Rapol, he is developing a strontium lattice clock. That's a neutral atom clock. So we have a plan to connect these two institutes using a fiber and phase stabilize them. It's only 3 kilometers away. We are 3 kilometers away from each other. So this is kind of a pilot work of phase stabilization that we plan for. We want to stabilize this 3 kilometer fiber and compare both of our clocks, and strontium and ytterbium is a very good combination of atomic clocks. So once we are there, a novel several novel things can be done using these two clocks. And then in furthest future, we also want to develop a cheap ion trap. Particularly, we are interested to develop a compact optical clock that is particularly for space use. But these cheap ion traps can be used for also for quantum computers, trapped ion quantum computers, which I am not working, but the other people can take the designs and use it for. But that's a very complex systems to develop. So this is our very, very long-term plan and scope, what we can do at IUCAA, and we are planning for. So thank you for your attention.
Thank you, Dr. Dev, for this nice talk, and just emphasized about the the applications of atomic clocks, especially to study the fundamental physics. So there is a question now by Mr. Pranav. So let me read it for you. So he's saying that all time measurements involve a start and stop signal in the atomic clock. Since you are talking of 10⁻⁹ accuracy, clearly no optoelectronic device can match this. Then wouldn't your start or stop signal essentially generate using some optoelectronic device, say laser, not give you errors of much higher orders? This is similar to how a person stopping a stopwatch will be limited by his reflexes. Did you understand the question?
Well,
Subhadeep?
partially. Maybe I can guess what he is meaning.
I think
there in the chart.
I'm going to answer this question in my next talk. So yeah,
Okay.
yeah,
I see.
my talk is about this only. So yeah.
Okay. So then there is also question in YouTube by Dr. Subrat Sarangi. He said that could we see some comparative results? Okay, this is for the actually the previous speaker. So this will talk discuss again in the end of the presentation. This is not relevant for this. And okay, so with this, so let us thank Dr. Subhadeep Dev for doing this wonderful work at IUCAA, and I wish all the best because he's now building up the lab, I think, because he just joined there recently. Now we'll go for the next talk. Again, this is on atomic clock, but it's a different atomic clock called active atomic clock. So Dr. Bindya Arora, so she did her bachelor's and master's from Punjab University, Chandigarh, and she was also gold medalist. Then she went to US for doing a PhD from University of Delaware. And then she was a postdoc at IISER Mohali for some time, I think just almost 1.5 years or almost 2 years. After that, she joined as an assistant professor at Guru Nanak Dev University, Department of Physics. And she has been chosen among the top 3 women scientists in India by NASI Scopus in 2019. And she was awarded Young Scientist Award by the Punjab Science Congress in 2012. And her research interest lies on atomic and optical frequency standards, quantum computation, and high precision calculations of atomic properties, and so on. And she likes to promote science among school children. That is one of the most, it's an important thing for us. And she has been also a long-term collaborator of mine. So with this brief introduction, let me now, request Dr. Arora to share the screen and present the talk. Yeah, please go ahead.
Thank you so much, Vijay. Thanks a lot for such a nice introduction. So I also thank all the organizers for giving me this opportunity. So let me share my presentation. Okay. Yes. So is the PPT visible to all?
Yes.
Yeah.
We can.
All right.
Yeah.
Great. So I would start by saying that building better clocks has always been a fascinating challenge for scientists and engineers, as Dr. Subhadeep just mentioned. In this talk, I would talk about important steps that have been taken to build better clocks based on active working principle. So these clocks are different from the clocks which Dr. Subhadeep was talking about. this is the outline of the talk. I would briefly discuss what atomic clocks are and what are their impacts, societal impacts and the scientific impact, how to build better clocks, and how active clocks can actually lead to more stable clocks. This is the main topic I want to cover. And our recent work where we proposed using a cesium atom for building a 4-level active atomic clock. So I have kept my talk very simple, and I'm going to discuss our results in very brief. More of the talk is more general for the general audience. So an atomic clock works like a conventional clock with atomic transitions as its timekeeping elements instead of oscillating mass as in the conventional pendulum clock. And as Dr. Subhadeep said, that these clocks are far more precise than conventional clocks because atomic oscillations have much higher frequency and they are more stable. And since its development in 1955, the first microwave clock has made enormous contribution to the scientific research and development. Then there was another generation of higher performing clock, which was the main topic of our previous presentation, which are based on the optical transitions. And they are expected to achieve fractional uncertainty above 10 to the power minus 18 level. Recently, a lot of attention has been given to clocks that utilize optical stimulated emission from ultra narrow atomic transitions in bad cavity regime. And this could actually reduce the influence of vibrations of the cavity mirrors on the emitting optical frequency. So this is what I'm going to concentrate on more in my talk. Okay, so why we actually need hyper accurate clocks? Biggest impact is the global positioning system. The GPS, it's a network of satellites so that several of them are essentially always in view. And a GPS signal on Earth compares different signal from the GPS satellites and uses that information to calculate exactly where on Earth it is located. And these satellites, they carry one or more atomic clocks, and a tiny instability in these orbiting clocks could actually lead to a few meters of error in GPS measurements. So our goal is to make these clocks more small so that they can in these satellites and increase their stability so that we can reduce the errors to fractions of a meter. Accurate and stable clocks, they also space versions. We need faster way for the ID without sending Earth, which is called on the other hand, on how the signal from the Earth and determine its location using clock on the surface of the Earth. And system, it actually supports human exploration and it avoids delays. Atomic clocks are benefiting to society. They help us in weather forecasting, measuring content of moisture, monitoring sea levels. Without atomic clocks, internet will not be synchronized, and they have a lot of military applications as well. So they have applications in fundamental sciences as well, as Dr. Subhadeep just discussed in great detail. Within the area of fundamental sciences, they can be used to test general theory of relativity, measure redshifts, and search for drifts in fundamental constants. And also they are used for benchmark calculations. Here I just briefly want to mention that IRNSS, Indian Regional Navigation Satellite System, is being developed by India. And at present, ISRO is importing atomic clocks from, I think, European aerospace manufacturers. I am not sure exactly. But it's in ISRO's mission to develop their own atomic clocks. And with NPL New Delhi, they are collaborating to develop their clocks for space missions. And NPL at present is trying to develop more accurate clock at optical wavelength based on single ytterbium ion. So clock, what is a clock? Actually, it's a device in which motion or events, they occur repeatedly. And then there's a mechanism which can keep count of these repetitions. For example, in pendulum clock, the motion is the swinging of the pendulum. And the clock device is an escapement. The counting device is the gear system mechanism that converts the swings into the position of the hands on the clock. In atomic clocks, the repeated event is the quantum analog to the physical motion of an atom. And this quantum analog is actually the transition between two atomic energy levels. So what we need is a local oscillator which can be adjusted to this frequency. And once there's a match of frequency between the local oscillator frequency and the frequency of the transition of the atom, what we do is we count the number of cycles of the oscillation electronically. So why we use atom as a reference of frequency? As mentioned in our previous talk, one atom is exactly identical to other atom of the same species. So when an atom is excited by an external energy source, it goes to a higher energy state. And then from this state, it comes back to the lower energy state. And in this transition, atom releases energy at a very precise frequency, which is the characteristic of the type of the atom which we are using. And if we build a device that registers this frequency of natural oscillation of the atom, all such devices, they are going to run at exactly same frequency. So basic principle or the requirement for building a clock is that we need a sample of atoms. We need an apparatus which produces oscillatory signals, and the frequency of these oscillatory signal should be in resonance with the atom's natural oscillation. And then we simply count the cycles of these oscillatory signal. So stability of these clocks largely depend on the stability of the oscillator which we are using to register this natural frequency of oscillation of atoms. So what can be used as an oscillator? And we know that light is a very good example of an oscillator. One can use lasers which have extremely regular oscillations as the local oscillator for atomic clocks. The basic working principle would be that we have a clock, a local oscillator which generates signals and sees if the atoms, they absorb this signal or not. And then we adjust this frequency of the oscillation so as to maximize the absorption. Once maximum absorption is observed, one can count the number of oscillators of a local oscillator. So the current definition of our clock is actually of our second unit is duration of almost 1 billion times of the radiation corresponding to transition between the two hyperfine levels of ground state of a cesium atom. Okay, so this actually is the basic working of the clock. I can quickly go through it. What actually is here is the atoms which are heated in oven and then bundled up into beam. And each of these atoms can actually exist in two states, at state A and state B. What we do is, what experimentalists do is, they have a magnetic field which removes all atoms in state B from the beam. Only atoms in state they are remained. The state A atoms, they are sent through a resonator where they are subjected to microwave radiations. This triggers some of the atoms to change their state to state B. And then we have a detector here that counts all the atoms that have changed to state B. The percentage of the atoms which have changed their state while passing through the resonator depends on how well the microwave frequency is in sync with the natural oscillation frequency of the atom. And our goal is to perfectly tune this microwave frequency with the natural oscillation frequency of the atom and then measure it. This slide we have already seen in our previous talk. What I want to emphasize here is that since the advent of clocks from the Egyptian era, Galileo's pendulum, marine watches, a lot of steps have been taken to build better and better clocks. Like cesium clock in Colorado is one of the world's most precise clocks. And there's always a thrive to build better, stable, and more accurate clocks. How can one build better clocks? So there are two factors or two terms which characterize the clock. One is stability and the other is uncertainty. Stability is a measure of precision with which we can measure a quantity, and it is quantized in the term of something called quality factor. This quality factor is ratio of the central frequency of the reference, which in this case is the atomic transition, to the spread in the frequency. So in order to build stable clocks, what we need is to increase the Q factor. And obviously, this Q factor can be increased either by increasing the frequency or by reducing the line width. So I'm going to press upon both these aspects in my coming slide, how to increase nu and decrease delta nu. So as I mentioned, a significant improvement in frequency standard is possible with the use of transition at higher frequencies, and frequencies of transition in optical regime are 5 orders of magnitude larger than the microwave transition frequencies. Thus, theoretically, they are possible. It's possible to reach the uncertainty of 10 to the power minus 18. And this was discussed in our previous talk. Elements being scrutinized for making these optical clocks are ytterbium ion atom, calcium ion atom, and so on. And they offer to build better clocks. Now, the next factor which can increase the quality of the clock is decreasing the line width. And the current theoretical limit of line width of the clock transition is in sub-millihertz level, as mentioned in previous talk. But we cannot reach this line width of sub-millihertz level due to the current, using the current laser technology. The scientific and commercial lasers which are used to register the frequency of transition, they store the coherence in the cavity field. Thus, the frequency of the laser is actually sensitive to the fluctuations in the cavity length. And it puts a limit to the line width of the laser source. Shen and his co-workers from Peking University in 2005, they proposed a solution, they proposed an alternate, I would say, to this. And this alternate was being used in these measures for a long time. What they suggested was, they suggested to use atoms with narrow line width transition as a lasing gain medium to build lasers with narrow line widths. So this system actually not only acts as a laser source with super narrow line width, but since lasing medium itself is the atomic reference, it can also act as a clock of high stability. And these clocks are termed as active clocks. In active clocks, we can say that high stability is achieved since there are no external oscillators as compared to the passive clocks, and instead oscillations are generated inside the system itself. So some advantages, as I mentioned, that the coherence in case of active clocks is stored within the gain medium. So they are largely insensitive to the fluctuations in the cavity length. And in addition to acting as a laser system, they actually can also act as a optical clock of high stability. Different approaches have been tried to create these high stable active optical frequency standards, such as neutral atoms with 2-level configurations, 3-level energy structures. Currently, we are also exploring use of highly charged ions as well. So one can simply understand, simply use this classical 3-level laser theory to understand the working of active clocks. To construct a 3-level laser, one uses of effective pumping from ground to excited state, from where the atoms spontaneously decay to one of the lasing states. Once population inversion is realized, lasing signal is produced. But the problem with such schemes is that since the pumping state and one of the lasing states, they are common, the stability and accuracy of the clocks is critically obstructed by the light shifts caused by the pumping laser. So to solve this problem, the alternate is to use 4-level clocks. In this 4-level clock, the pumping is from state 0 to state 3, and the clock lasing is between state 2 and state 1. Since they are different, it will reduce the effect of light shift caused by the pumping laser on lasing state. And the requirements to build these 4-level active clocks is that the lasing excited state 2 should have longer lifetime as compared to the lower state 1. And obviously, we should have accessible lasers for cooling and pumping. So this is the energy level for the cesium clock. We used the same principle to explore the feasibility of building an active atomic clock using trapped cesium atoms in one-dimensional optical lattices. This is the schematic energy level diagram. Here, a 455 nanometer pump is used to populate cesium atom from ground to excited 7p3/2 state. Subsequently, these atoms decay to 7s/2 state, which is one of the lasing state or the clock transition state. And at that time, a mode of cavity is adjusted to couple with the 7s to 6p3/2 transition. The main purpose is to attain stimulated emission and produce lasing signal. And thereafter, the atoms, they decay to the ground state and hence completing one full cycle. And this supports a continuous lasing signal. Now, the second factor which makes better clocks is to decrease the uncertainty in the clock. And uncertainty, if we try to understand, is how well we understand the physical process or the transition that can shift the measured frequency from its unperturbed natural atomic frequency. So what happens is that there are many sources of errors that can creep in, and these errors can perturb the atomic system, which is that our frequency reference. Perturbations like magnetic field, electric field, thermal radiations, etc. They can perturb the system, and the external perturbation can cause the shifts in the actual clock transition. And there are two ways to decrease this uncertainty. One is to reduce this shift itself by using some experimental tricks. And the other is to calculate these shifts and then compensate the measured frequency by this amount to find the actual unperturbed transition frequency. So let me first give you an example of how we can reduce these shifts. For example, the shifts caused due to the motion of atoms can be reduced by trapping them in optical lattices. So optical lattices use 6 laser beams to create pattern of standing electromagnetic wave, and this creates series of energy wells, each of which can support one atom. It only does not reduce the shifts due to atomic motion, which are called the Doppler shifts. This arrangement also prevents electromagnetic field of individual atom to interfere with those of the neighbors, and thus allows oscillating signal of many atoms to be measured at once. But there is one problem associated with atoms which are trapped in optical lattices. That is the potential experienced by the two clock states is different, which may lead to stark shift of the clock transition. A solution to this problem, it was proposed by Katori and his co-workers, who proposed to tune the wavelength of the laser light to a wavelength where atom experiences same optical potential irrespective of in which clock transition state it is present. And this optical trapping potential, it depends on the atomic polarizability, and this is where accurate atomic physics calculations, they play a very important role. One can accurately calculate these polarizabilities using a number of methods available. In our group, we use sum over state approach to calculate polarizability using all order method. So in sum over state approach, the polarizability can be written as a sum over intermediate state which are allowed by the dipole selection rules. These here are the reduced dipole matrix elements. The advantage of using sum over state approach is that you can replace these theoretical energies by the more accurate experimental energies to get better numbers. So here I would like to say that the most challenging task which was involved in our proposal for the cesium active clock was to calculate these polarizabilities with high accuracy, since we are talking about polarizability for two excited states which has not been explored by a number of people. These are the results for the static dipole polarizability for the lasing state 7s. And as you can see here, 7s state has transition for 6p half and 6p3 half, and the convergence is very good, which means that the low lying states, they contribute significantly, and the high lying state contribution which is included in this tail part is very small. And then these are the dipole polarizability result for the 6p3 half state, and 6p3 half state has contributions from scalar and tensor part as well. These are the scalar contributions, and it has contributions from 6p3 half has contributions from S and D3 half, D5 half states. And similarly, these are the tensor contributions for the second lasing state. Now, since we know how to calculate these polarizabilities at static value, we can do similar calculations which are going to give us wavelength dependent dynamic polarizabilities for the two states involved in our clock transition. And once atomic polarizability for these two states is calculated as a function of wavelength, it is easy to locate the wavelength at which these atomic polarizabilities match. So these are the magic wavelength results for our cesium clock proposal. And as you can see here, the red curve is the polarizability for 7s half state. And since 7.5 state is a high excited state, it was very difficult to estimate its polarizability, especially in the vicinity of these high-lying resonances, these Rydberg states. And the blue and the green curve are the polarizabilities for the 6p3 state, that is the second clock transition state, which is MF dependent. And as you can see here, we managed to have a lot of magic wavelengths, but these magic wavelengths are of very limited experimental use since they are very close to resonance. And we managed to find a magic wavelength around 1181 nanometer, which is going to support the clock transition for this particular proposal. Okay. Now, since this clock operation, it does not only involve 7s and 6p3 state, it involves other states, which are the states involved.
May I request you to wind up the talk in 5 minutes?
Yes, sure. So other states which are involved in cooling, pumping, and repumping also are present. What we need is that this particular magic wavelength of 1181 nanometer should also support a strong trap for these states. And as you can see here, the dynamic polarizabilities for these states is positive, and it is it's very large. They support a red-detuned trap. The main problem was to calculate the polarizability for 7p3 state. As you can see here, in this range, 7p3 state has number of resonances, and it was very, very difficult to actually calculate this polarizability. And I would be happy to share more details how it was done if somebody is interested. So the next way to decrease the uncertainty in our clocks is to accurately calculate these uncertainties and then compensate for it. So the ideal definition of clock, it occurs at natural unperturbed transition of the atom. However, the external perturbations are always present in real experimental setup. So transition frequency should be accounted for the effect of these external perturbations. And external perturbations can be due to magnetic field, electric field, thermal radiations, which cause shifts like Zeeman shifts, quadratic Stark shifts, and so on. So what we can do is we can accurately calculate these shifts in the clock transition caused due to these external perturbations, and then compensate it for to find the actual unperturbed frequency of transition. So I'll give you one example here. It's the blackbody radiation shift, which is one of the major contributors to the uncertainty budget of clocks, most of the clocks. The ideal definition of second is given at 0 Kelvin, whereas actual experiments, they occur at mostly at room temperature. So the transition frequency should be corrected to take into account the effect of blackbody radiation. And blackbody radiation, it actually creates a temperature-dependent electric field described by the Planck's law. This electric field causes temperature-dependent frequency shift of the atomic transition, which can be written in terms of static polarizability. So we atomic theorists are very well versed how to calculate these polarizabilities, as I showed in my previous talk, and we can calculate these shifts very accurately. So this is the fractional frequency shift for cesium active clock. These are the BBR shift, the quadratic star shift due to pumping and repumping lasers, second order Zeeman shift. And the numbers, they don't look very impressive, but by conducting experiments at a lower temperature and by controlling laser power and calculating the polarizabilities more precisely, we predict to achieve fractional uncertainty to this clock proposal at the level of 10 to the power minus 15. The catch point of this proposal is that the line width of few tens of millihertz is achieved by using these clocks. So I come to the conclusion that we worked on a possibility of using cesium atom to construct a 4-level active atomic clock. A magic wavelength was calculated. We gave an estimation of fractional uncertainty. And right now we are exploring how highly charged ions can offer better stability and accuracy to these clocks. In the end, I would just like to mention the role of atomic physicists. This is an online portal. It's not relevant to the talk which I just showed, but this is something I would like to publicize. It is being done with my collaborators in US, and we are actually working on an online portal for high precision atomic data computation, and it has data for these 16 elements right now, and we are planning to increase it. And this data has all the transition rates, matrix elements, and polarizability. So we are going to make it public in a day or two, and I'll be happy to share the website with you all to get your feedbacks. So thank you so very much.
Yeah, thank you, Dr. Arora, for this very beautiful talk. So now let us go to this question hour session. So we have a very active participant, Mr. Yas. So he has actually several questions for all the speakers, but we have not taken all, and also he has a question for you. So his question is, in the 4-level clock, what about metastable states?
So the requirement is not metastable state. As I said, the requirement is that the higher excited state should have lifetime more than the lower lasing state. Yeah, that is one of the requirements for lasers, I would say, in order to get population inversion. Otherwise, the lasing action will not occur.
Okay, so then there is a question by Mr. Somaranjan Jhankar, who is asking, when two particles collide in LHC, can we use this clock to take care or measure of their time of contact?
Okay, that is a question which needs.
Okay, so the answer to that question is yes. So actually, in LHC, people use atomic clock, primary atomic clock, and here we are just trying to find out alternative atomic clock, better atomic clock. So like as the previous speaker spoke, so if you have a more precise atomic clock, so that means some more signals can be identified in LHC. So the answer is yes. And the next question is by Malika Singhal from PRL. She's asking, what is the counting mechanism in atomic clocks? Like gears are used in mass pendulum clocks.
Okay, optoelectron, when you use these lasers to actually first would say sync your oscillation, and then counting mechanism. I think Subhadev would be able to this frequency comms. I think they are used as the counting mechanism. If I'm not if I'm incorrect, Subhadev can correct me. So yeah, what we need in atomic clocks is a frequency reference and an oscillator. We need the oscillator and the frequency resonance, frequency reference in resonance, and then we obviously need a counting. And mostly, I think these frequency comms are used as a counting mechanism. I might be wrong.
So basically, detectors are used to see the number of atoms being excited. So that is in the passive clocks. Here, so another mechanism is basically detectors are used to count the number of atoms, exciting from ground to excited state and falling back.
But here, I think she's talking about how to measure the oscillations in the oscillator, local oscillator. I think that is the question. So that should be done using frequency comms.
Reference. Yeah. Okay. So that's all for this one. Okay. Thank you, Dr. Arora, for this nice talk. And now we'll move to the next speaker.
Thank you so much.
So we have the next speaker is from PRL itself. So Dr. Rajesh Kushwaha. So Dr. Kushwaha did his BSc and MSc from Banaras University. And after that, he had joined PRL as a PhD student, and he continued his PhD from 2004 to 2009. And after that, he was also postdoc at PRL for 2 years. And then he moved to Europe for 3 years for doing postdocs. And he was at Lund University, Sweden, and also at UPMC Paris. And then he had come back in 2013 to India, and he worked as an assistant professor at IIT Ram, Ahmedabad. But then he changed his mind and he went back to US in 2014. And he worked there as research associate for 2 years. Then he returned back to India and joined PRL. And he's currently working as assistant professor in AMO-PH division, PRL. With this brief introduction, now let me request Dr. Kushwaha to present his talk. Can you share your slide, Rajesh? Rajesh, can you hear me? Bhusit, are you there?
Yes.
Rajesh is there, but his mic is unmute. Where is Rajesh? He's connected from 2 IDs.
Oh, yeah, hello. Yeah, sharing is not possible from my side. Is it possible to?
Can you send your file to Bhusit immediately?
I have shared. I have already shared.
Are you connected from 2 IDs?
Yeah, now it's possible to share.
Yeah, please. You can share. I have enabled. Because of
Okay.
2 ID, there was some confusion.
Yeah, I think it's visible to all of you.
Yes.
Yes.
Hello.
Yeah, go ahead, Rajesh.
Just
Yeah, Rajesh, go ahead, please.
am I audible? Yeah.
Yes, you are audible.
Yeah. So yes. So I would like to thank organizer for giving me a opportunity to share my research activities. Just a minute. My video is on or not?
Video is on.
Yes. Yes. So I will be talking about quantum control of molecular dynamics and reaction, and I'm going to share recent results from newly developed lab. So let's see what new results we got. So first, I would like to start very basic about the atoms and molecules. So atomic, molecular, and optical physics is the central to many branches of science. It is a fundamental science. You can see that it is central to like nanoscience, forensic, chemistry. You can name many. Okay, and even it is in fundamental in nature, but it has given many kind of technology development. It has given idea. It has given understanding. You can count from the X-ray, laser, and many more. And in this era, the new technology and science is called the attosecond science. So in this subject, how and what we study. So we try to study the atoms and molecules and their process using a kind of experiment that is called the collision experiment. So what we do is we take atoms and molecules, and we are interested to see what is the nature of that atoms and molecule, what is the energy, how the dynamics is inside the atoms and molecule. So we use some kind of projectile, let's say photon, electron, or ion, and then collide them, and after that we measure them. So we cannot directly look what is happening in this regime. What we see is that we measure the cross section, means the particles which are coming out from the atoms or scattering, and then we plot it, and then try to interpret what happened inside the atomic system and molecular system. This is a very unique way, means even after 100 years of this branch of science, atomic and molecular physics or quantum mechanics, still we are going in the same way. If I ask what happened in this region, let's say, we don't have direct way to see that. What we have is the indirect way, means we see where is the peak, where is the cross section, and try to assume, I mean, interpret based on the theoretical understanding. But let me just see that in this region, what is the time domain? Let's say if this is a photon and if it's taking time, so what is the time domain this happen, and is it possible to see by eye? Let's say, can you see that, okay, how electron is jumping from one state to other state by eye in a slow motion? We don't want to go in a something that, okay, something's happen and we measure and then we saw the this is because of the electron transition. We are interested to see inside the atoms when this process happen, and how you can do that. This is a challenge, and this is our objective of our lab. I'm going to explain later. Let me introduce the another field, let's say kind of chemistry, or this experiments you all familiar, in which this is a famous breakthrough experiment, Miller-Urey experiment. It is even in the textbook, in which there is a mixture of gases in the primitive condition, where sparking happened, and then they put a few gases and then left for a few days, and after a few days they found that there is a formation of amino acid. So it is a kind of breakthrough. Yes, it is certainly a breakthrough, but what we learn out of this, we mix the two things or three things or four things, and then you get some result. Let us see what are the challenging questions that we have not understood yet. So let's say atomic system. Let's try to understand this system or the previous system, like I have shown. Let's say atomic, simple atom. The size of atom is order of 1 angstrom, and if light pass by this, so what will be the pass by time or interaction time? That we can divide by simple mathematics, distance by the velocity, and we will find out it is order of 10 to power 18 femtosecond. 18 seconds. So it is attosecond time scale. Means when the light interact with atomic and molecular system, the electron response is in attosecond. Nuclear vibration is picosecond to femtosecond. Many processes happen even here, that is bond formation, bond breakup, change of molecular geometry, many things happen. But this intermediate state is not known to us. What is known to us is the end result, means we found the some molecules, and that is amino acid, and that is breakthrough. What we are interested is to know what mechanism happen and how you can control them. And if you know that, then it is possible that you can make molecules as per our demand, as per interest. So then this is going to open a new branches of science that is called molecular engineering. So in PRL, in PRL, I have developed a lab to probe the electron dynamics in the attosecond and the nuclear dynamics in picosecond to femtosecond time domain, and to know both information. Both information means the structural changes and dynamics. Both information we want to know same times. If you see the literature, either you can know the structure or you can know the dynamics by some different kind of spectroscopy. Both we cannot know. There is no techniques through which both information you can know. And if you know both information, then it's called the molecular movie. So whatever the time domain process happen, in PRL we are developing the lab, that is we are saying femtoscope and attoscope. Femtoscope is functional, through which we can make the molecules. We can control the molecular dynamics. We can make a new molecules. We can know the full information how the molecules is behaving under the perturbation. So this is about the objectives of my lab. Let me go in the next stage, what I am going to discuss today. So I am going to discuss about the quantum control of molecular reaction. I am also going to introduce PRL Quantum Science and Technology program, and we are working on the molecular qubit. So briefly I will introduce my approach, how we are going to make a molecular qubit. So let me see what is the quantum control. If electron is moving here or there, can you control that? Yes, by using electric field or magnetic field you can control that. We cannot say that it is a quantum control. Quantum control means in the atoms, in the bound state, if you excite the electrons to some state and then try to control their before its decay. So decay may be happen in very fast time. Nuclear decay may happen very fast. Fragmentation may happen in case of molecules. So we want to control even in the bound state. As I said in the beginning, that electron lifetime or electron time in the atoms or molecules is in the order of attosecond. We need a tool in order of same time, attosecond kind of pulse to control them. Or in molecules, we need if molecular time is pico and femtosecond, we need a tool to control this dynamics, and that tool be the same time or is better or even smaller time than the what molecule nuclear is motion is. So when I say quantum control, it means we are controlling the electron and nuclear dynamics, which is in bound state. Also the molecular rotation and vibration, they also behave like a quantum mechanical system. You know the rotational and vibrational wave packet. So we probe the molecular wave packet. So let me just propose what are the scheme that already exist and how we are approaching. So let's say we pump to the some excited state, and then this is a called wave packet. It has some decay time. If there is no other pulse, this wave packet decay, and let's say this blue one is the yield. So if AB molecules are there, it break to the A plus and B plus. That yield is always there for given perturbation, for given energy state. But if you want to control the yield, let's say you want to change the yield, then you try to kind of perturb this dynamics before the decay happens. So if this decay is, let's say, 100 femtosecond, before the 100 femtosecond this decay completely, this molecules, we have to perturb that. So this is a one way that we can perturb the molecular wave packet, and then we try to change the yield. The another way is we can try to perturb the potential. Let's say each atom or molecules has Coulomb potential. So when you increase the laser field, and if laser field is strong enough to order of, let's say, Coulomb potential of atoms or molecules, then Coulomb potential will perturb. If Coulomb potential will perturb, then what happens? The electron tunneling happen, and then this is a picture of three-step model in which the tunnel electrons will gain energy from the laser field, because laser field is still present, and then combine, and then the energy will transfer to the XUV photon. This XUV is an attosecond source. This is a method through which attosecond source has been achieved. What I am talking about the quantum control of reaction means to control the electron dynamics. Let's say electron is recollision, further excitation happen. Let's control the electron recollision so that the yield will be different. So this is our scheme, and based on that, with this objective, we started performing experiments. So let me show on which sample we have performed. So we have used the polyatomic molecules, methanol and CH3Cl. We use the femtosecond pulses, and then we change the various parameters so that we can control the yield, and we measure the yield of S3 and S2. If you measure the Cl or OS, it is like a bond breakup, but we have a focus on the bond association, which is unexpected when you perturbing the molecules, because we are breaking the bond and then bond formation happen. But so we are even interested to control the bond formation during the bond breakup process or during the interaction. So let me just show, this is our lab that I have developed in PRL, and this setup we have used in this research, which is a velocity map imaging spectrometer, and we have used the time of flight mode to investigate the bond association process and its control. So this is a schematic of setup. We have used the laser, femto laser. This is a specification. We have used both OPA, optical parametric amplifier, that is giving 1100 to 2600 nanometer, and as well as the fundamental 800 nanometer. Both we are focusing in the molecular beam. Then in the, we are detecting by MCP detector. So we have a time of flight spectrum. And now we are changing the various parameters so that we control the yield. So let's see what are the scheme. So one scheme is, let's say we change the laser parameters, like intensity. So we see the intensity is different, and you can see that H2 and S3, their yield is changing. So why this is happening? Because we are perturbing harder and harder. It means we are populating to more excited state, and as a result, this is giving a signature that more H plus H2 and S3 formation is there. So we then study that how much it is changing or what is the trend. So we change the intensity, laser intensity, both for linear. LP means linear polarized and CP is circular polarized, and you can see that they have increasing trend. So this is a one way that we can easily know that it's like use this laser and this much yield we can get. So this is a one way that we can perturb or change the yield of the molecular reaction. Let me choose another one. Let's say we change the pulse width. So here you see the 29 femtosecond and 195 femtosecond. And when you change here, you can see even the doubly ionization process happen. This is happened because the laser is in the field, your molecules is in the field, and in the field it's like your laser is acting like a potential. So the energy needed for multiple ionization is now shifted, it will be reduced. So that's why this process happened. There are other interpretation are already there in the literature. But what we see here is a very clear signature that even the pulse stretching is changing. And how much is changing, you can see here. We have changed the pulse stretching in this milicos, and you see this changing a lot. So this is another kind of findings that pulse stretching can be used to control the yield of particular fragments. Let me show the some other results where we have changed the wavelength. The wavelength at the same intensity, the effect is reverse. So once you go, let's say, higher wavelength, then the yield is going down. This is normalized yield. So you can see with respect to total counts, it's going down. So this is another one, because this is happening because at the same intensity, low, this wavelength means low energy. So we are not assessing the higher excited state, so that's why the yield is going down. This way you can try to interpret. So for given this case at two different wavelength, again you just check how the wavelength, how the intensity is changing. So as a function of intensity, how the yield is changing, and you can see they have a very unique pattern. This is a region is not clear to us, but we found this one by repeating a multiple times experiment. Still we found this kind of profile. This is still not clear to us. Let me just show another one. So let me see here the linear polarized case at 1300 and the circular polarized case, and you can clearly see the yield is going down. So how to interpret that? In the beginning, I saw that when you increase the intensity, then tunnel electrons happen, and that recollide happen, and then recollision electrons will also produce the excite the molecules to some higher excited state. Once you change the polarization, we are basically changing the electron trajectory. This is in the tunneling regime. We are using the photon energy, which is in tunneling regime. So basically, we are perturbing the Coulomb potential. Electron is tunnel out, and then this electrons is colliding to the molecules in this case, and then we have a huge this fragments. But that fragments is going down once you change the polarization to linear to circular. To investigate further how this polarization is basically influencing and what are the mechanisms. So as I said, the electrons can recollide and then excite the molecules. There is a phenomena that is known as the non-sequential double ionization. So the electrons is recolliding. It has is kind of coupling between the other atomic system and this electron. So while it's scattering is excite or is take another electrons, this is kind of non-sequential process. So that process can also happen. So we have investigated here, and you can see that this is, let's say we are changing the linear polarization to circular polarization, and then the trend we can clearly see. So here our tunnel electrons is also contributing in the reaction, means formation of S plus, S2 and S3 plus. But that tunnel electrons once change the polarization here, circular, that effect is down. So basically we are reducing the non-sequential double ionization process. We can confirm this one by, let's say, checking the doubly ionized case. So doubly ionization case is down here, and it is more here in both cases at two different power. It means that this non-sequential double ionization cross section, which is higher here, is suppressing a lot, means electron recollision, and then non-sequential double ionization process is going down. This is the way we have used to change the yield of the various dissociative channel in the molecules. So this is a summary that I have shown in a very simple way, that we have changed the control the electron trajectory in the process and change the yield. So this is a one way that we can control the molecular reaction, unimolecular reaction. Let me introduce other research activities that we have recently started once our lab functional. And Professor R.P. Singh has already introduced that PRL has a big team on quantum science and technology, many experimental and theoretical team, and they are working on this. Yes, we are both experimental front and a theoretical front. We have taken initiative in this. So in our femto lab, we are basically working on the molecular qubit, and we are trying to understand how our quantum control, let's say, I explain that in a very simple way. It is not, I should explain the, let's say, wave packet dynamics and then other control method. I just explain the very recent result. But we have a capability to control the electron dynamics, ion dynamics, control the wave packet. So can you use that in the field of quantum, let's say computing, so, or develop some kind of molecular qubit? So already Professor Bhanu Pratap has introduced that there is a quantum classical bit, like the classical bit, there is a quantum bit, and any two-level system can be considered as a quantum bit, and then you can use like electron spin. The only difference here is the that in quantum nature, it is a superposition of states. So both state is possible. I have already given many presentation on Schrodinger cat experiment that I have performed about many years ago, to 2015. As well as you can find other experiments where double slit experiment or probing the wave packet that I have performed. You can see the details. So we have capability to generate and probe the cat state, let me say, or entangled state in the molecules. So this we are exploiting, means this we are going to use in finding the, let's say, molecular qubit. So let me see what are the, I mean, what are the search, what are the kind of, like we said, any bit, any two-level system, either spin or polarization or many things we can consider can be suitable for qubit, okay, quantum qubit. At present, this is a status, the superconducting qubit, that is also called transmon, that has been already developed in lab, and IBM, Google, and other giant industrialists, they have already started. They develop basically artificial atom built from the neodymium and aluminum, and then that atom is behaving like a spin up or down, basically a qubit. So already this is in progress. Other many groups in the world, they are using like a spin in the molecules, a magnetic system, either solid state system, like quantum dots or defect center, NV center, you may be aware. So many people has working on this topic also, that they basically, this is like people are trying to find a suitable qubit, and already introduced trap atoms or ions as a qubit, or silicon spin qubits, that is basically a quantum dots kind of things, and polarization. So at present, this is a scenario. Why? I mean, none of them are very suitable. See, on paper and theory point of view, you can assume this is a qubit and this is a computation you can do. But when it's come to experiment, when you come to realization, the lifetime of that state matter, and the lifetime of all the qubits are very short. Why? Because of that is impact by the atmosphere. Many things can influence the their state. So the superposition of state, that is an integral part of our qubit, that may be perturbed. And already you see here that entangled state or cat state that we have learned, that will be, once you perturb, means we lost the information. Okay, so that is called the decoherence. The loss of information is defined as a decoherence, and then there is a method, theoretical, lot of code has been developed that how to correct it, or how much the decoherence is there. As for the current status, the microsecond molecular qubit, that is lifetime is microsecond, and recently Chinese group claimed that they have generated a molecular qubit of the order of millisecond lifetime. So this kind of claim and research is still going on. What we are working is that we are getting motivated from the paper that is again proposed by John Preskill, Caltech State University, Caltech, yeah, Caltech. So he proposed that molecular rotation can be used as a robust kind of qubit correction. Means we can use the molecular rotation, either alignment, to impose our information on the molecular rotation, and then these days it is possible to align molecules in a controlled way. So if there is a loss of information, let's say you can put in this way, if there is a loss of information, that can be corrected by the some developed method. So this is what he proposed. So that the idea is already, I mean, last 10 years, you can see the molecular qubit research is going on, and on many molecules, this realization has been done. But this is a kind of first proposal that molecular rotation has been proposed that can be used to act like a molecular qubit. Either molecular alignment or anti-alignment can be considered as a 0 or 1, or the molecular, let's say, angular momentum. So molecular has once it's rotating, it has different angular momentum. So it's possible that molecules are superposition of all the angular momentum, and then when you measure, you will know the particular state. So these are the kind of potential, I mean, potential candidate for molecular qubit, and this has been recently proposed. We have experimentally aligned the molecules. So this is a polarization axis, and many molecules we have aligned, and then there's a anti-alignment also. So we are trying to conduct a research that can you use our alignment method, in which you can correct the molecular let's say decoherence if there's a loss. Usually this is a, let's say, in picosecond time domain. Even if you measure microsecond time domain, there's no loss unless there's something interact here. But if there is a scheme like proposed by the Prescale, that if you know that how much there is a loss, then it will be very useful that we use molecules as a potential candidate, or is a suitable candidate for molecular qubit. So we are working on this. The another, I have not discussed this one, but we are working in our lab using the pump probe scheme to probe the molecular wave packet. The first scheme, like I discussed, to probe the molecular wave packet and control the yield. There has been proposal that if there is a molecules in which there is a degenerate state or conical intersection, that state is basically represented as a cat state. Means is a superposition of both cat live or dead state, and unless we measure, so we don't know at which state this cat is. So this kind of state has been proposed, and we have already performed experiment to probe the molecular wave packet. Already I have given references on CO2, how to probe the molecular wave packet of CO2. So we are working that can you use this idea to have a suitable molecular qubit in this direction. With this, I would like to acknowledge and thanks my team, and thank you.
Thanks a lot, Rajesh. Finishing the talk in time, perfectly in time. So we have a question for you from Mr. Samyaranjan Jhankar. He's asking, is your quantum control framework enhance the bioinformatics field, oncology, etc.? I don't know. Is your quantum control framework enhance the bioinformatics field? He's asking that whether you can use quantum control technique in other fields like bioinformatics or something.
Yes, sir. So let's say the main aim of quantum control of molecular reaction is to control the yield. Yield of reaction means, let's say you are interested to make a new molecules. Your aim is to make a molecules, or as per the requirements, either biology or chemistry or pharmaceutical or even the quantum computer. Let's say if there is a need that we have to probe, we have to know that how the atoms is changing in time, or how what process happening. Can you control that? Once we have that information, we can control, and this once we have this ability, we can use in any field, including bio. I hope I have answered, because I am not aware of many quantum bioinformatics problem. But yes, this is a general, we are working on the general problem, means it is suitable for all.
Okay, so there is one more question by Mr. Baravallia. So he wants to know whether molecular qubit has a value of average of all rotational value of atom, or any particular rotational value, or it has both the value. I don't understand this.
Okay, okay. So,
you understand this?
Yeah, let me just say. So this is a proposal. Let's say in the your setup we align the molecules, but we don't know molecules is aligning or anti-aligning. So can you consider that is like a quantum qubit? Okay, it's a superposition of both states. This is a one. Second is like once we talk about the molecular orientation or rotation, it is like associated with orbital angular momentum. So it has many angular momentum, and unless you take a projection or measurement, we don't know and which state it is. So this is a proposal that we can use this as a qubit because we can correct it. At present, in many labs, we can control the molecular orientation or direction. Other case where let's say NV field, quantum dot or NV defect or other method, there is no way to correct it. This is what proposal made by the Preskill.
Okay, thank you, Rajesh. It was very nice talk. So now let us move to the last talk of the session. So the last speaker is Dr. Bodhaditya Santra. So he had the same like trail like Dr. Subhadeep Dey. So he did his BSc from University of Bardhaman and then MSc from IIT Kharagpur and went to University of Groningen for doing PhD. And after that, he did his first postdoc in Technical University in Kaiserslautern, Germany. And then he was also a postdoc at University of Hamburg. And then he was also a postdoc at senior postdoc at University of Innsbruck. Then he came back to India. Now, right now, he's at Department of Physics of IIT Delhi. So he has started many new experiments in India, mostly related to quantum technology and sciences. So now with this brief words, let me now request Dr. Bodhaditya Santra to present his talk.
Thank you very much for the invitation and for the kind introduction. Let me share my screen. So it says that we cannot display your shared content. Makes your
Can you send your
you
file
have allowed
to
permission.
Yeah, can you send your file to Bhusit or me? You have Bhusit email ID. Actually, he had requested all of you to send talk file to him.
Oh, do not work. Let me just try. You can be saying on Keynote.
Can you try to share again?
Yeah, I have to make this permission. Security
sorry, Bhusit, are you there? Can you help Bodha?
Yeah. No, that internally he has to get the permission. Are you using MacBook?
Yes.
Yeah. So then initially also this issue was there with some speakers.
Yeah.
So you have to set the permission and then re-log in.
Yeah, I'm just trying. Is it? Or from do I have to change? It's from accessibility.
Bodha, when you click on it, Mac, it asks you to unlock it. And then you have to click that you are giving permission to Cisco. You have to tick there.
So why do I have to go? I go to the system preference and then security and privacy.
Yes, and the security, just unlock the security option and tick the Cisco WebEx Like, I'm sure there should be a lot of, what do you say, permissions given to other applications. So you have to include WebEx in that permission list by ticking it.
Yeah, somehow it's not appearing here.
To save the time, you can share the file either with me or Vijay, so we can start
Yeah.
sharing.
Okay, let me do that. I have to convert it into PDF and then send it to you.
You can send PPT file also. Anything is fine.
I have a keynote once. It's oversized. I think it's oversized, that's why it's not going. But I cannot see this WebEx thing coming up here. Even if I open this. I should click on this accessibility, right? I see many
Yes.
things, but not WebEx.
You can see either Cisco from Cisco WebEx.
This I do not see. Maybe I can add it.
Bodha, are you trying to, when you try to share, then the Cisco WebEx automatically opens a pop-up window where you can give permission. So you don't have to go to the settings.
Correct.
It was not doing so. Let me try it again. Try to
Yeah.
save it again.
The window which says shares, the WebEx window which says shares, around there you have to click somewhere, then it asks that WebEx doesn't have permission. So if you click on it, a pop-up window is open.
Allow pop-up first, yeah.
Yeah.
It's not opening.
Allow pop-up.
Then it will not.
Oh, no. Let me compress this PDF and then send this.
But you told that you have used Cisco WebEx earlier.
Yes,
Bodha.
yes. I don't know why this is not working this time. I'm compressing this PDF file and then sending it. Now I can see Cisco. I'm going to send this compressed file to
Split into two parts and send the file.
I have compressed it already. I'm sending it to Dr. Bhusit.
So actually, Bhusit had emailed everyone to share the file, but it was.
I have sent it now.
Actually, this WebEx has this problem actually.
I have allowed it now, but then also it does not allow me. I don't know why. Dr. Bhusit, have you received my email?
Bhusit, are you there?
Yeah, just received. Let me download and unpress it.
Okay.
Yes, sorry for this delay. So we'll just start immediately.
Just give me 2 minutes. I am opening the file.
Okay. Okay.
Sometimes it is difficult to trust this technical technical stuff. Yeah, no, I think
Actually, now I have also given permission, so this part, but then also it doesn't allow me. Why?
Okay, no
Yeah,
problem.
for that, yeah, you have to log in again. But I think Bhushit already has your talk now.
Yeah, I have already sent it to.
I think.
Okay. Fine.
Is it visible to all?
Yes, yes.
Okay. Is it going to YouTube as well?
There is a time delay. Just wait. I think whether you start, so
Yeah.
the YouTube,
Okay.
yeah, there also it's visible, so you can go ahead.
Okay.
Yeah,
Okay.
go ahead.
So really very sorry for this glitch, unwanted, heavily. And I'd like to thank you very much, all the organizers, for inviting me for this special occasion. And yeah, so I'm going to talk about cold atom quantum technologies. So I work with atoms and lasers. I use lasers for cooling atoms. So the picture, what you see, that contains a glass cell, which has a very ultra high vacuum. So the pressure inside is 10 to the power minus 11 millibars. So that is 14 order of magnitude lower pressure compared to what we feel in the atmosphere. And at the central part, this green blob, what you see, this is the fluorescence from one of the intercombination transition in ytterbium atom. So that's at 556 nanometers. So for whatever we do using cold atom quantum technology, this is our starting point. And now if we change atom, naturally it's the frequency changes, and that's how the color changes. But the basic mechanism is same. So, okay, can you please change the slide? Okay, thank you. So, yeah, so before going into the technical details, so let us have a look at what kind of impact we can have in our social lifestyle if we have quantum mechanics into play. So there could be several things. If you think of in the summer, there are in many places sometimes power cuts, and even into rural villages, so getting power in a uncut way is a challenge. So one of the main reasons for that is the lack of total amount of power. So now how to take care of that? So imagine when this electricity goes through resistive wires, there is a lot of drop of electricity. So a lot of misuse of power. So if you can invent some wires which has very low loss, we could reduce this this loss from the grid to the households or to the any industry. So that could help us a lot to make a better power availability in our society and in industry. So that is one of the unique example. And besides that also, so one of the reason why we are getting smartphone today, if you think of computers, one of its early version, it would come in the size of a full room, and now we can put them in our pockets. The main reason is because we can make very, very good materials. And then also comes about the drug design. So the drug design is basically finding a good combination of atoms which can make a molecule which could combat some type of specific diseases. So that's also kind of a very challenging and optimization problem. But it also has a demand that you cannot really wait for a long time. You have to find a solution in a very, very short time. There are many other problems like the optimization of flight paths, or whenever we put some this mobile or telephone towers, how to put that in a most optimized way in the domain of secure quantum communication. So normally all the computation, quantum computation can be done using static qubits, but how to transfer those information over a long distance? So we need for photons for that as a flying qubit. And how do we make this information transfer from atom to photon? So kind of this atom photon or static qubit to flying qubit coupling. There is another very important aspect about sensing. So sensing can be enhanced using quantum effects. It can be atomic clocks, as some of the speakers already mentioned, or it can be quantum interferometer based on atoms, or it can be magnetometer based on atomic vapor, and all those things, this quantum mechanical effects enhance the sensitivity of measurements. And that helps a lot in several areas of our modern lifestyle. And how can we address such aspects using cold atoms? Can you please change the slide? Yeah, thank you. So the first one, or what you can see, so this is a realization of Fermi-Hubbard model. So for that, we can first start with some atoms which are at a room temperature. You should know that at room temperature, atoms move with a velocity of a jet plane. So it's really very fast. It's more than 300 meters per second. And then as we use lasers, so normally lasers are used for heating. So how can we cool them? So we can choose some specific frequencies, which is normally blue detuned. This means the frequency of the laser should be slightly higher than the frequency of the main transition. And then we can cool them, the atoms, to few microkelvin levels. And from there, we can cool them even further to few nanokelvin levels to form a Bose-Einstein condensate or a degenerate Fermi gas. And then we can load them into optical lattices. So the optical lattices are formed by standing waves. We can make 1D, 2D, and 3D like a periodic potentials. And then if we start with fermions, then due to the Fermi exclusion principle, so there will be a formation of the up-down kind of arrangement, which are the first basis of forming the antiferromagnetic order. And now if we study those things, if we look into the phase diagram, then the phase diagram of such Fermi-Hubbard model provides the clue of how to get a superconducting behavior of such wires, which could be very useful for transporting power. And also, if we load the atoms at a very low temperature to specific lattice sites, like the triangular lattice, then you could explore various types of topological properties. And today's talk, there was various times mentioned of quantum computing and quantum annealing. But one thing we should also should not forget, at least at the research level, that we should try to make qubits out of topological properties. Because if we can make such qubits, then this topology is not a local property; it's a global property. So then this type of qubits would be much less prone to the environmental decoherence. And quite naturally, the coherence time and many other very static, very strange requirements can be simplified. And we can also make single molecules on demand just by combining two atoms. That the picture what you see on the very right side, these are two single atoms. One is sodium and one is cesium. We can combine them on a deterministic way, and then we can really study the chemical reaction behind it. It might sound very simple, but if we start with a very simple experiment and then make our model, then we can step by step increase the complexity and go towards a more and more complex molecule. What you see in the left side bottom, that is an array of about 49 single trapped atoms. So one of the challenge in quantum computing using cold atom was the following. So when we load the atoms into the optical traps, this loading process is probabilistic. But now for making a quantum computing, we need a defect-free array of qubits. So how do we do that? So this problem was addressed just by last few years. So what we do is the following. So we first start, so let's imagine that you would like to fill an array of 10 by 10 qubits. And what we do is the following. We start with a 20 by 20. So this means we have almost 400 sites which can be occupied by atoms, single atoms. And out of that, roughly 50% would be filled. And then in a second step, we took some moving tweezers, moving optical tweezers, and we pick some of the atoms from the outer side, and then we fill it a central part of this 20 by 20, and then we make a defect-free array of 10 by 10, so let's say 100 atoms. And that gives a very good platform for exploring various types of quantum algorithms, which are necessary for either quantum optimization problems or quantum annealing problems or universal quantum computing. And then comes this atom-photon coupling. There could be various types of atom-photon coupling. It could be free space, or it could be coupled with the evolution wave, which could come out of a nanofiber. And then comes the optical clock or the optical interferometer. So which are starting with the cold atoms and then performing different kinds of interferometry and then giving the either the frequency. So there are some questions just some time ago that how do you measure the frequency? So I will show one result where you can see that basically this frequency is related to time in an inverse manner. And then if we measure the frequency, if we do the spectroscopy, then we can indirectly measure the time also. So this fundamental quantity what we measure is frequency. So now let me go a little bit deep into the talk. Can you please change the slide? Okay, so in the first part, I'll be discussing about quantum state engineering by control dissipation. So it was already pointed out by Professor Das and many other speakers today that decoherence is one of the biggest adversary to any quantum process. Now, we just want to have a look if we can use it for anything good purpose and if we can turn its role from a bad to a good. So I will talk about this first, and then I will show some results on clock spectroscopy. So how to measure the frequency with a very precision level. And then I will show one or two slides on quantum computing with neutral atoms, what we have started building here at IIT Delhi. So can you please go to the next slide? Okay, yeah. So one more next, please. Yes. So now when we talk about dissipation, so this is actually an opposite effect compared to the coherent phenomena. So now you can imagine a system which has a gain and which has a loss. So it can be imagined just if you take a simple water bottle and if you make a hole at the very bottom, and at the very top part, if you add a inlet, so then you will have an inflow and outflow. So such problems are not only in the quantum domain, but very general for any kind of classical system. It could be in a heat conduction problem, or it could be in any kind of current flow, or it could be even in a share market. So such a system with a gain and loss constitutes a non-equilibrium system. And when this gain and loss balances each other exactly, the system forms a steady state. So now there are a couple of proposals. So can you please go to the next page? Yeah. Okay. So now there are a couple of theoretical proposals which are showing that if such a dissipation channel is present in the quantum system already from the very beginning as a static parameter, then after some time, this whole dynamics after this transit time drives the system to a steady state. And now this steady state would be much less prone towards any kind of environmental decoherence. So it would form a very robust quantum state. And now if we can characterize and realize such states in our lab, either it's a DEC system or it's even a single qubit system, then we can use this system as a starting point of any kind of quantum algorithm or any kind of protocol which requires pristine quantum states. And such a phenomena can be modeled with this following equation. So you see this density matrix. So it has this normal Hamiltonian plus there is a term L. This is actually a Lindblad form. So this involves this dissipative mechanism. We could model that using some Liouvillean operators. And in the real life, there could be different ways of modeling it. Either we could make some non-resonant heating, or maybe parametric heating, or we could make some deterministic atom loss. So can you please go to the next slide? Yes. So this particular experiment. So what I'm going to show, this is where we have combined a scanning electron microscope with a Bose-Einstein condensate of rubidium atom. So can you please go one more slide? Yeah, thank you. Yeah, so what you see here on this right side bottom, so these are the atoms loaded into a 2D lattice. So when we load atoms into 2D lattice, we get an 2D array of this pairs of atoms. So each of these pair has about 80 atoms, and then we make the picture from the top. So that's why each of them looks like dot. It's actually integrated over a line. And now the distance between each two dots is about 600 nanometer. And in the next picture, what you see, where we have written this H psi equals to E psi, we have deterministically removed almost all the atoms from these sides. So this picture we did just to demonstrate how precisely we can create localized dissipation. But now in the next slides, I'm going to show you how we use this to create an initial state of our dissipative quantum system, and then we looked into the steady states. So, okay, yeah. So now what you see here, so this is the time scale dynamics of our system. So we first started with a rubidium BEC, and then we loaded it into 1D optical lattice. So when we loaded it into 1D optical lattice, so we had a series of kind of 2D systems now, because this 1D standing wave that would make a series of 2D potentials. So you can think of just taking a laser beam and then put a mirror in the opposite side and get it reflected back. So that will make a standing wave. And in the nodes and antinodes, depending on the frequency and wavelength of the laser, you can trap atoms. So that's how we did that. And then we increase the power of this laser too high so that there is almost no tunneling. And in that situation, we depleted almost all the atoms from one of the sides. And after creating that initial state, we reduce the power of this laser so that tunneling among the between the these lattice sites can start to happen. And then we looked into the dynamics. After that, we take a picture. So we just freeze the dynamics again, and then we make a scanning electron microscopy picture, and then we looked into what kind of time evolution happened for this empty site. So now let me see if I can go to the next slide. Okay, yes. So now what you see here, so this green dots and the red dots, these two are exactly the same experiment I told you, but with two different initial conditions. So for the red dot, we have completely depleted all the atoms at the beginning. So that's initial condition 1. And then for the blue dot, so we did not deplete any atom. So that's the initial condition 2. And you see that for both cases, after some transient time, which is around 100 millisecond in that order, so that both the states reached a new state, which is a steady state. And now this experiment we did for one specific dissipation, which was very low. So let me go to the next slide. Okay, yeah. So if you look into this this plot, so where we have plotted dissipation strength in the horizontal axis and in the vertical axis, the filling levels are there. So the last example what I showed here, these were coming from the very left side, so the very low dissipation. So this behavior is almost like a superfluid behavior, because whatever we do to the system very fast comes back to its initial state. And now if we look into the very high dissipation strength, so that is around the more than 200 or so. So then also both the initial steady state goes to a same or similar final steady state, but this is different from the superfluid behavior. This is more or less like a resistive behavior. So if you send a current through a resistive wire, then you will get a voltage drop. So this behavior is similar to that. But now interesting thing happens at the intermediate dissipation. You see that just depending on the initial state, we can drive the system to two different steady states. So you could see that so we have not done anything else. We have just added a dissipation. We have changed this parameter in a controlled way, and then we are able to create different kinds of steady states. So this means it is possible to create steady states on demand. So I think this is a very important tool. If we could implement a similar thing for the case of, for example, single qubits or maybe for quantum memory, because in all these systems, dissipation is the biggest problem. And now if we know that just using a dissipation channel from the very beginning, we can make a initial state, which is not an equilibrium state, but which is a steady state. But this is good enough and very robust for any kind of environmental decoherence. Then we have a already very good starting for doing the further jobs into the quantum protocol. Okay, now let me change the gear a little bit. So far I was talking about the atoms. The rubidium, which is the alkali atom, has one electron in the outermost orbit. Now let's add one more electron in the last orbit. So then we would have alkali earth atom or alkali earth like atom. So here I am talking about the ytterbium atoms. It's a fermion. It has also bosonic isotopes. And the main the attraction of these atoms comes from these states, these p states, mostly this triplet p1, triplet p0 states. And in particular, this triplet p0 state has a very long lifetime. So we can use it as a kind of a second ground state. And that is why this is the state which is used for building the best clock in the world. So this atom also can be used for studying various types of many-body physics and doing many kinds of precision experiments. So here you see this circular type of picture. This is a time-of-flight image of a degenerate Fermi gas when it was released from a optical dipole trap. And then when you loaded this degenerate Fermi gas into a triangular lattice, and then we make a time-of-flight image, the first Brillouin zone was populated. And then in the lower this picture, you can see 6 different spin components. And now we can use these 6 different spin components as a pseudo spin for studying many kinds of many-body physics. It can be a 2-orbital SUN magnetism, or any kind of Kondo lattice model, or topological superfluidity, or even spin orbit coupled quantum dashes. So that is why such an experiment, such an atom provides really a rich variety of possibility of studying physics. Okay. Okay. And now, so I just mentioned you this this core part of this triplet P0, the clock state. But now, I mean, we saw that this atom is very beautiful. But to get advantage of this beauty, the main thing what we have to do, we have to get this clock laser operating in our lab. And this is actually the heart of this type of experiment. And what you see in this picture in the right side, this is how it looks like. And Professor Bharadwaj was mentioning at the very beginning that today physics is not just physics, it's just quantum physics, and it has many other aspects which are directly connected to it, like mechanical engineering, electrical engineering, electronics engineering. So that the main technology, what you need to build such a clock is building a very stable cavity. And the main question comes that how can we narrow down the laser? So you can have a look at this left side. So this is just a Fabry-Pérot cavity. And if you send the light through a Fabry-Pérot cavity, you know that there would be a very narrow frequency window through which light would be transmitted. So this could be very low. And that is only for one solid. But now, if you keep on doing this measurement, due to the thermal change and all other vibration, so the cavity length can change. So what happens, this narrow window, this will keep on changing. So that would effectively broaden the line width of this very narrow laser also. So how can we combat that thing? So we can fix if we can fix the length of this cavity, then so this narrow window would be fixed. And that's how the long-term drifts can be reduced. So that is why when we build such cavities, we just put it inside some vacuum chamber, and it's also shielded by several layers of thermal shielding. And also we make active thermal stabilization. And then we can find out what is the critical temperature where the expansion of this ultra-low expansion glass is minimum, and we can set the temperature of this cavity at that point. And then for whatever change happens in the environment due to the the temperature changes or any other thing changes, then the cavity length stays more or less constant. So that is the main trick behind such experiment. So if I go to one slide, the next slide. Yeah, maybe one, two more slides. Just want to go back one slide. Yes. So how do we measure this zero crossing? So what we do is that we just change the temperature just by manually a little bit, and then we wait for the thermalization. And you see that in such a very good isolated system, so it takes really several days to get the temperature stabilized. So you can see how good the thermal isolation is there. And after reaching that, we change a little bit again, and that's how we collect a couple of data points corresponding to temperature and corresponding frequencies. So for this, we kind of make a bit note of this light which is going through the cavity with an optical frequency comb, so that we can precisely measure how much frequency is changing due to certain change of temperature. So that already provides us a characterization for this cavity, and then we know at which temperature we should fix the temperature of our cavity, so that we get the minimal frequency change due to the change in due to any change in temperature. So after locking our laser to this cavity, so let me go to the next slide. Okay. Yes. So after locking the laser to this cavity, we did the just one sweep, single sweep. Then we get the full width half maximum of the laser, which is just below 1 hertz. It's just something around 0.8 or something.
May I request you to wind up the talk in 5 minutes?
Okay, sure. Yeah, I'm almost at the end. Yeah. Okay. And now if the thing what I was mentioning that is visible in the right side, if we now keep on doing this in a cycle, then if we make the average over 30 seconds, then you see the full width half maxima increases from below 1 hertz to like 4 point something hertz. And as good as you can make this the lock, then this deviation would be better and better. Of course, we take some extra precaution. We make some compensation due to drifts. That is also another characterization. Okay. So now let me show you the measurement of frequency. So let me go to the next slide. Okay, so I'm not going to this slide. This is about how we can make the optical lattices. but I'll go to the next slide. Yes. So here what you can see that you remember, so I was showing this 6 different spin components. So here we had spin polarized the Fermi gas. This means we have pumped all other components to one of the component. This is corresponding to MF equals to plus 5. And then we did clock spectroscopy of this ultra cold Fermi gas with only one spin component. If we do that, you see this spectrum has a full width half maximum of 50 Hertz. So this is one of the, so this is close to one of the very good clocks worldwide. And as our main motivation was not to build a clock, but as to do many body physics using such ultra narrow transitions. So this would provide us a very good knob for probing such many body physics using such atomic clocks. And now if we add another spin component, so if I go to the next slide. Yes, so if I now add another spin component, then you can see both the spin components, so minus 5 up and plus 5 up on both sides. But at the center, you can see this little peak. This is actually coming from the strong interaction between these two fermionic species. So they are same species, but they have two different spins. So such a platform provides the possibility to study spectral line-shape spin orbit coupling using clock transition and preparation of specific quantum state. So now if I go to the next slide and one more. Okay, so now I'd like to spend maybe a few minutes about quantum computing using single trap neutral atoms. So the effort what we are doing it here in our lab. So some of the key advantages of using neutral atoms are the following. So these are identical qubits, which is of course same for ions. This is a gift from nature because all our qubits are that they're real atoms. We don't have to fabricate. And then the miniaturization. So this is, I think, unique for cold atom because even for ions, so one can make like 70 to 100 probably. This would be the number of ions in one Paul trap. And now, if we would like to extend, if you'd like to scale up the system, so you have to, of course, either extend this or you have to add several Paul traps. And there is another factor, which is basically these ions are, they are always connected by Coulomb interaction. And one has to also map the background Hamiltonian for that. But for the case of atoms, they are individually trapped by optical features. And whenever you would like to switch on interaction, we can really do it in a very much deterministic way, just by applying these two photon Rydberg excitation schemes. So yeah, so that those things provide some very good edge of ultra cold atoms, so all other existing technologies. There is some other requirement like the large dilution refrigerator is not needed for ultra cold atoms, which is the case for superconducting qubits. And ultra cold atoms, as they are not charged particles, they are comparatively less sensitive to the environmental noises like this spray magnetic field or spray electric fields. So that is one of the reasons they also provide very good coherence time compared to other systems. And for last couple of years, there are also a lot of startups which are coming up. So here, this Science magazine also put up some article which was pointing out that neutral atoms are rising as a dark first qubit candidate. And there were a couple of startups like Cold Quanta, Atom Computing, Pascal, and then QEra. And we are aiming to target the problems mostly which are in the quantum optimization domain. It could be a traveling salesman problem or quantum drug design problem. And main challenge is to develop the quantum algorithm, which is not so trivial. And like very similar to the classical computer, if you have a hardware and if we do not have the software, then this computer is more or less useless. But that is the main reason why we do need to develop quantum software with a very good priority list, similar to the hardware development. And it was really nice to see that were some of the first talks that they are developing this quantum software. And with that, I'd like to go to the next slide. Okay, maybe one more. Okay, so in my talk today, I tried to convince you that ultra-cooled atoms cooled by lasers provide a very good and versatile toolbox for implementing different kinds of quantum technologies, starting from quantum computing, communication, to quantum sensing and metrology. And there are so many things. We have just started working in this field. So just remember that laser cooling happened only around 1985 and BC 95, and then first trapping in optical potentials is around 2002. And after that, we are busy in doing quantum simulation of various interesting things. And now recently, we have also started looking into quantum computing and communication schemes. So I am very much looking forward to this exciting field. And here in IIT Delhi, we have also, can you please go one more slide? So we have also started building our lab, and you can see all these enthusiastic people. It's really amazing to work with them, and they are putting their day and night effort to build each component. So we are not only looking into the physics, but also mechanical engineering, electrical engineering, also data acquisition systems, and many other things. And it's really amazing to work with them. And I'm really very much looking forward to get some good results in coming days. And with that, can you please go to one more slide? Yeah, thank you very much for your attention.
So thank you, Bodho. So you have a very big team, I know, so early. Okay, so it was a wonderful talk, and it now we come to end of the session. So there are a few questions for you, Bodho. So let me read them for you. So one question is from Mr. Soumyaranjan Jhankar. So he's asking, let's say we trap an ion in a Paul trap. This means we make our position somehow very precise. Again, we are using laser cooling to minimize its momentum. That is micromotion and let us say in atomic clock, which means we try to make the momentum precise. Is it violating uncertainty principle or not?
I think so. There are two things. So the one is position, fixing it in the position, and the other thing is when this particle, it could be ions or atom or anything, but you could take a simple picture of a harmonic oscillator, and if you think of any particle, so it's a harmonic oscillator problem, and it's not necessary that if you fix the particle in a position, its position into this harmonic oscillator state would be always at the ground state. It could be also placed at a higher state. It would be related to its energy. And now by laser cooling, what we do is that we try to, bring down this system to its the lowest possible, we call it a quantum ground state of the harmonic oscillator. I hope it provides answer to your question.
Okay, so there is a question by Mr. Partha Raul. He is asking, nanotechnology is an application of quantum physics in a simpler way. What is the relation between nanotechnology and quantum computing?
Yeah, I think this is if we can make it even more clear, it would be both the platforms can be benefited a lot. I think in the nanoscience, there are so many materials. There are some of the examples I was showing in the very first thing. So these materials, they have lattices. So, and now how to model these materials? So that is, I think, one of the main questions. And now you might know that modeling such materials using a classical computer, if you go beyond few electrons, so just imagine like 8 or 10 lattice sites, and if you fill the electrons, and then it would take enormous time. And that is one of the reasons why Feynman was suggesting, what about taking quantum particles, put them into the artificial lattice, and then do the experiment and then look at the result. So I think in this way, both fields can benefit from each other.
Okay, so there is a question by Dr. Subhadeep there. So he wants to know why the spectra corresponding to +5 and -5 have, I think, I don't know which ion it is. I think ytterbium ion or something like that.
Ytterbium atom. Ytterbium atom.
Have a kilohertz line width when the clock laser is less than 1 hertz line width.
Yeah, so the point is that what we did here, this is something in a spectroscopy in a clock, in a lattice, 3D lattice. And then you have to really do the Fourier transform of the pi pulse what we send. So this pi pulse has a shape of like this rectangular, and what we get is a sinc function. and that is why we get this line shape. And the another thing, it also has to do with this natural frequency and many other things. So that kind of broadens this. And we cannot really do spectroscopy at the moment, not better than this limit. At least this is my understanding. Maybe he has a better idea with his single atom.
So there is a question by Dr. Arco Rai from Italy. So he is asking, do you always need a lattice to be able to do quantum computation with cold atoms? Can't it be done in continuum, that is without lattice?
Depends on the requirement. So for example, if you want to implement quantum memory, then you might get even advantage if you do not do in the lattice, because if you have an ensemble of atoms, you will get a collective enhancement of quantum effects. But for example, if you would like to really encode qubits, then yeah, probably going with the single particle level is better, because there you can control the interaction in a much more precise way, right? So I think so.
So there is a question, I think last question by Yas, because he has asked several questions today. So which technology you use for separate a single atom?
Okay, yeah, so this is a very fundamental and very good question. We are basically at the moment working on this only. So first step is to laser cool and trap atoms using a magneto-optical trap. So there we can reach temperatures below 10 microkelvin. And once we have that reservoir of atoms, we adiabatically switch on an array of, the array of optical tweezers. So these optical tweezers are very focused lights. So you can assume them as a optical dipole traps, but with a very low waste. So around 1 micrometer or something. And now when they have a trapping depth, which is large enough means it has to be larger than the kinetic energy of the atom. This means if you talk in terms of temperature, and if the temperature of the atoms are, let's say, 2 microkelvin, and if you have a tweezer which has a corresponding trap depth of 1 millikelvin, so the atom from the reservoir to the tweezer would be transferred. And then we can adiabatically switch off the Mott lights and fields, and then what you will have an array of tweezers filled with single atoms.
Okay. So there is a question, but it's out of the theme, that is, can we do quantum simulation using BEC-BCS crossover? I think it's out of theme, so let's not discuss this one. So Bodha, I would like to thank you for giving nice talks and answering all the questions. There are two more like general questions, so it's actually I had told everybody that we'll have questions like left for the other speakers. So may I request Bindya to answer one of the questions Pranam had asked that was not answered. And another question that I would like to put it to Professor Das, that there is a question that how much probabilistic the quantum mechanics is. So maybe I will request first Bindya, can you just answer the question that Pranam had asked?
Regarding the starting and stopping, was that the question?
Yes.
Yeah, I answered that in the chat window. So I'm not sure if it is correct. I think, yeah, there should be some effect. Maybe Subhadeep has also tried to answer it by saying that they do it, the laser pulse is continuous and it's not like they are doing it as a pulse laser. So there is no need to operate electronics or optoelectronics accessories at ultra short time scale. I'm not sure in what context he has written this answer, but I think yes, this is a problem where to start and end your count oscillation, but this is where active clocks are better, because the oscillator and the reference itself is the atom. So you don't have to see where to start and stop your clock.
Okay, so thank you, Dr.
May I interrupt? Can I give the answer once more?
Yeah, go ahead.
So I think here is a misunderstanding. When the atom and photon are interacting, we don't send a pulse of laser light so that the atom can interact with that pulse. If that is the case, then you have to make sure that the pulse is starting at a particular time and ending at a particular time. In this case, everything is continuous. Continuous means laser is on always, atom is there always. They are always interacting each with other. And the time here is actually coming from the lifetime of the excited state, but atom photon interaction is always on. So The
Okay.
accessories like optics or optomechanics don't need to have any switching for that.
Okay, thank you, Dr. De. So now I'll leave one question to Professor Das to answer. That is, how much probabilistic is the quantum mechanics? Allowing that, I will also request him to give a concluding remarks and summarize the talks we had today, all the wonderful talks we had today. So may I request Professor Das to come online and say a few words?
Okay, thank you. Now, about the question, how probabilistic is quantum mechanics? Well, I would say that it's entirely probabilistic. It's intrinsically a probabilistic theory. Probability is built into quantum mechanics. Well, there can be situations where you can make predictions with 100% probability, like, for example, in quantum entanglement. There are situations if you know the state of one of the qubits, then you can know the state of the second qubit with 100% certainty. But, yeah, in general, it is a probabilistic theory in a very intrinsic way. So that's all that I can say about, how probabilistic quantum mechanics is.
Thank you very much. So could you please kindly conclude the scientific session part?
Okay, so let me begin by thanking all the organizers of this meeting. I think it was a really great meeting, a unique meeting. And I feel a little awkward because I was one of the speakers. And, so, what can I say about
You are the most experienced and
Okay,
we
all
want
right.
actually you want
Yeah,
want to have your experience. So you
Okay,
want
all
to
right.
say
Okay. Yes, thank you. I'll try. Well, I think this, as I said, I'm just repeating myself, this meeting was really excellent, unique. And it covered frontier areas of atomic, molecular, and optical sciences, quantum computing, atomic clocks, quantum control of molecular dynamics, and cold atom quantum technologies. These are undoubtedly in the forefront of AMO sciences. So instead of commenting on the specifics of the talks, let me just say a few things. I think what these talks have highlighted is that it is important for experimentalists and theorists to collaborate. So that is clearly evident from all the talks. The very fact that we had 3 experimentalists and 3 theorists, and each of the talks had an experimental and a theoretical aspect, means that this collaboration is important. And what I would also say is that I think we should take this opportunity to form some kind of a network, first within the country, and then, of course, we will expand. I think we could call this as quantum science and technology, atomic, molecular, optical sciences network. It's a long name, QSTAMO, but I think it's worth it. And I would suggest that, two persons from here could be the coordinators, 1 theorist and 1 experimentalist. Certainly not me, but someone younger and someone more dynamic, I think. So let's start on that right away. Let's form a network of AMO scientists who would focus on quantum science and technology. Okay. Now let this begin from within the country. And we can, identify people. It's open to anyone. And so let's start with that. It's open to faculty members, to postdocs, to students. So we can make a beginning by, contacting groups in this country where, AMO sciences are pursued, and, mention our objectives. This is to sort of promote collaboration in these areas. And we can start having these kinds of meetings, and there, of course, we can, invite speakers from abroad. I mean, if we have a meeting of this kind, um, we can certainly have speakers from abroad who we think will help in furthering our research, you see. And then perhaps we can, also have collaborations with groups outside of India. Now, I would also suggest that we include, and that was really evident from many of the talks, including the last talk by Dr. Buddhaditya Santra, is that this sort of goes beyond physics and chemistry, and it includes other areas, like, for example, high performance computing, computer science, different branches of engineering, and mathematics. We should also try to involve people from those communities in our collaboration. Could be within the country, could be outside the country. And I think that is what we should sort of, aim for. And each of these areas, whether it is, quantum computing or atomic clocks or quantum control of molecular dynamics or cold atom quantum technologies, I think we should have people beyond the basic sciences, beyond physics and chemistry, have people from various aspects of computing, maths, and engineering. And so once we, form such a network, I think it'll be easier for us to choose problems that we can collaborate on. Now, once we've done this, it'll be easier also to apply for funding to the quantum technology mission that probably, I don't know what the exact status is, but I hope in a few years that will be active and fund projects. And we can also apply to departments or agencies that support research in these areas, like the Ministry of Information, that is MITI, that is Ministry of, I think it's Electronics and Information Technology. So they are supporting research on quantum computing and information. We can seek funding from them, you see. So these are some of the thoughts that I have. So I would urge us to use this opportunity to start such a network. And this will help for us to understand each other's work. And, it should be open to any institute, university in the country. I mean, there are efforts to start such activities. I mean, I know that IIT Tirupati has a Center for AMO Sciences and Technology. IIT Bhubaneswar is interested in certain aspects of quantum computing. So this is basically what I would like to say. Thank you very much.
Okay, thank you very much. So we'll consider your suggestions in a very positive way and try to work out towards that. May I request our director, Professor Anil Bharadwaj, to say a few words based on the comments Professor Das gave.
Thank you, Vijaya. And let me first of all thank all the speakers for their excellent talk. And very interactive sessions which went through for more than 4 hours now. And all the participants who are joining us live and taking part in this celebration, I should say, of Quantum Day. Also, thanks to the organizers, especially Vijaya and RP and Bhushit, for organizing this wonderful meeting, which has brought together people working in different domains of quantum science and technologies, theory as well as experiments. And I echo what Professor Bhanu Das was talking, is that theory and experiments has to go in together. And no doubt about it, it has to happen in all fields, and so it is in quantum science and technology. And there are many applications which looks to be going to emerge from this areas of quantum science, which will go into quantum technology. So there will be people who will be working on basic fundamental quantum science, and the application of that will go into technology and then probably into engineering aspects. And we are already seeing this trend in many areas, which will include communication areas, information area, computer areas, where this basic fundamental science which is coming out from quantum science going into engineering areas. And you probably, if things works out the way it is, there would be a revolution in terms of the way we do our information exchange or communication or computations. Certainly there is a need for networking, and I would urge the community to do excellent networking. ISRO itself has come out in a big way now, working in this domain, particularly looking at the space-bound quantum communication areas. And PRL, of course, is always committed into this areas of both science and technology of quantum, in terms of quantum science and quantum technology. So my best wishes to all of you, and also on celebrating the World Quantum Day today. Of course, because yesterday was a holiday for all of us, so we could organize it only today. And I convey my thanks to all the speakers once again, and to the organizer for this wonderful meeting. Thank you.
Thank you, Professor Bharat, for your wonderful sharing your views and suggesting us what to do next. May I request our Professor R.P. Singh to say a few words before Bhushit gives the words of thanks?
It was really nice to hear all the talks. They were quite interesting, and certainly the concluding remarks by Professor Bhanu Das, we should follow it up. We should not just listen and forget. Okay, we have to take concrete action on that, and PRL has to play a good, big role there. Okay, in networking, we have to. We have like very active group here, and we should network properly so that we can produce much better results. Yeah, to increase the visibility of this research. And certainly, Professor Bharadwaj was very graceful, and he, in the beginning itself, he very nicely pointed out how quantum science and technology is going to play a big role in society. He put it very nicely, very simply, in a very layman language. That was really interesting, and we are very thankful to him for giving so much of time. And thanks to all the speakers, all the participants. It's not easy to participate online meetings. They were there, present, hearing the talks, asking questions. So thank you, everybody. And with these words, I ask Bhushit to conclude the seminar meeting.
So it is my privilege to be part of this very novel and initiative celebration of World Quantum Day from PRL. First of all, I would like to thank our director, Professor Anil Bharadwaj, who at a very short notice approved this, activity. In fact, we sent an email and within half an hour we got an approval. So that is a great booster for all of us to go ahead. Probably myself and Dr. Sahu had a discussion that can we do it completely last maybe Thursday or Friday, and today we are here. And this is possible because of all the support we got from all the speakers, especially. We are thankful to all the speakers for their agreement at a very short notice. We are thankful to Professor R.P. Singh for his support. We are thankful to all the participants of this meeting through YouTube and WebEx who responded to our call and registered for the meeting, and they are still connected with us for more than 4 hours now. So I would like to thank once again all the entire team who helped us, and we look forward to the better event in future. And if possible, let us pray that it could be in person, and we get away with this challenging time. And may God bless everyone a very healthy time ahead. With this, I would like to conclude, and if anything, Vijay want to add. Nothing.
That's all. Okay, thank you, everybody. Take care, and see you again sometime soon. Yeah, bye bye.
See you.
Thank you.
Bye bye.
Bye bye. Bye.
Thank you.